early remote sensing studies. NRSC initiated a major effort in mapping surface water bodies at national level through development of automatic feature extraction techniques using multispectral data from multi-date IRS List 3 AWIFS datasets. Then we have metland mapping. We have vegetation laden swamps and wetlands form important constituents of natural ecosystems. Both reflective and thermal and infrared images are extensively used to map and monitor these water bodies. As part of this inland wetland mapping by ISRO RFCs, integrated land use, turbidity and aquatic vegetation maps were generated using multi-season IRS List 3 data. Wetland statistics were generated for all the 65 districts in Gujarat, Bihar, Jammu Kashmir, MP, Rajasthan, UP, Karnataka, Tamil Nadu and AP. Field data was integrated for prioritization of wetlands towards conservation planning as part of MOEF UNDP sponsored projects. Then we have the runoff and hydrological modeling. Rainfall runoff modeling has many applications like from basin level water source assessment, flood wave run simulation, flood protection designed to support downstream rescue and management, reservoir storage management, hydrological balance computation and climate change modeling. Then we have the irrigation water management. Investment and development of irrigation infrastructure has been long and continued priority in India. Programs such as Bharat Nirman, AIBP accelerate the irrigation potential creation and efforts are on for improving the performance of existing irrigation subsystems to bridge the gap between potential created and utilized and to improve overall water use efficiency productivity. Data collection in irrigation systems is well established practice to convertibility between available data and readily usable information is little. Advances in communication and remote sensing satellites provided many new opportunities to generate and transmit information on weather, water and agriculture. Use of satellite remote sensing data for IWM has been demonstrated through many studies. Inventory of irrigated agriculture. Mapping of cropping pattern and crop condition assessment using remote sensing data was carried out as early as during early 1990s after successful launch of first Indian remote sensing satellite RSA-1A in 1988. Mapping of crops in irrigation command area was carried out through visual interpretation of image prints to analyze of multispectral optical remote sensing data using various image processing algorithms and using microwave radar data. Various satellite derived indices have been used to evaluate crop condition. Some of the indices like NDVI were found to be directly related to crop yield and were thus used to estimation of the crop yield. Crop yield has been estimated for cereal crops like paddy. NRC also has executed various command area projects under National Water Resource Management Project and Water Resource Conservation Project. And this shows the inventory and monitoring of irrigated agriculture in Nagarjuna Sagar project of Krishna Delta, where the green is the paddy, the violet is the non-paddy, and blue is the non-paddy biseasonal. Salinity and water area mapping, waterlogged area mapping. Waterlogging and subsequent salinization and alkalinization are the major land degradation process operating upon the irrigation commands of the semi-arid regions. Due to improper management of soil, water and resources in the command areas, the problems of salinity and alkalinity and waterlogging are reported to be on increase. Among the new technologies developed for soil survey, remote sensing data from spaceborne sensors like Landsat, MSS, TM, IRS List 3, 123, SOSAT 1, SPOT, MLAPA provided to be valuable to map and monitor salt affected soils and waterlogged areas. Satellite data are being used regularly for mapping of salt affected soils. So the figure shows the data from IRS 1C List 3 PAN merge FCC, and this is the classified output where they have been classified as severely salt affected soils, moderately soil affected soils, slightly soil affected soils, waterlogged areas, water, cropland, orchards and settlements. So the salt affected soils can be classified. Then we have the reservoir sedimentation. The analysis of sedimentation rate of Indian reservoirs show that annual siltation rate has been generally 1.5 to 3 times more than the design rate, and the reservoirs are generally using capacity at the rate of 0.3 to 0.92% annually. Multi-temporal satellite data have been used as an aid to capacity survey of many reservoirs in a cost and time effective manner. While this technique helps in revising capacity table between minimum and maximum draw down level observed in the satellite data, loss of dead state capacity can be obtained only through conventional hydrographic surveys. A national action plan on sedimentation survey of 124 reservoirs using remote sensing technology has been taken by India during the 10th 5-year plan by the Ministry of Water Resources. And the figure shows here the reservoir capacity loss and sedimentation assessments for different reservoirs. Water harvesting for dryland agriculture has a traditional management technology to ease further future water scarcity in many arid and semi-arid regions of the world. Parameters for identification of suitable rainwater harvesting areas are rainfall, land use or vegetation cover, topography and terrain profile, soil type and soil depth. So these are the water harvesting structures planning using geospatial data of DEM, slope, classified slope, land use, soil texture, and then the buffer zone between the suitable and unsuitable zones are provided. Then we have the flood cyclone disaster support. The increasing frequency of occurrence of extreme events of the droughts and floods are posing great challenge to human society. And remote sensing data, both historical and near real time, provide objective and authentic information both on behavior and response of various activity to extreme water conditions. Such information is vital to create, understand and model the effects and formulate strategies to cope up with extreme weather conditions. The timeliness of satellite data has proved to be very critical in flood management, rescue operations, damage assessment, planning the floodplains and to formulate long-term strategies. Then we'll come to the future trend and prospects. The investment in science and technology, the communication facilities and the satellite technology and computer capabilities that have increased manifold since our independence have resulted in an explosion of quantum of data. The widely scattered large amount of information generated through various efforts have to be properly coordinated, coded and preserved using information system. The need for creating water databases are imminent and we can hardly afford to delay the matter. Natural Resources Information System, NR Census and National Spatial Data Initiative go a long way in addressing the data-related issues that emerge while preparing the roadmap for implementation of many water resource projects, including interlinking of rivers. And this is the conceptual framework of VARIS, India VARIS roadmap, which has been, data has been given. So with this, I end my presentation. Thank you.
Thank you, sir, for sharing your expertise with us. Let us invite to the stage the next presenter, Dr. Rajaram Purohit, Scientist D of Central Groundwater Board. Dr. Rajaram Purohit is a Scientist D at the State Unit Office in Agartala for the Central Groundwater Board. He specializes in hydrogeology and project management. He completed his education at various institutions in Odisha and Delhi, culminating in a PhD focused on arsenic contamination of groundwater. His work experience includes various roles within the CGWB, Ministry of Environment and Forest, and the World Bank Assisted National Hydrology Project. He has published numerous papers and reports showcasing his expertise in World Bank procurement procedure, project management, groundwater, and spring studies. Sir, the stage is yours.
Thank you. Good morning, everybody. I am Dr. Rajaram. I am from Central Groundwater Board, as he already introduced me. I have the privilege standing here because I have a little bit of contribution to this particular floor of this building. I was in NHP, National Hydrology Project, where we gave some grant to construct this building. So I am part of this building. I am part of this house. So let me take the opportunity. And again, I thank you all. Let me start with the presentation. Being the first presentation, we have some leverage that you can cover the entire topic. But here, there will be some repetition. But I will try to focus more on groundwater subject. To start with groundwater, when I say groundwater, through remote sensing, you directly cannot detect groundwater. There are indirect ways. Indirect ways means there will be soil moisture somewhere, there will be vegetation somewhere. Through those indirect method, you can start delineating to, okay, these are the zone where we get groundwater. So it's like the synthetic aperture radar, which slightly penetrates to the ground, that can give a slight hint on the groundwater level or the amount of groundwater available. But as on date, there is no direct method where no direct method where you can know about the groundwater. So let me start. My today's topic will be application of space technology on groundwater. To start with, why space technology? See, space technology has the advantage that in a limited capability, whereas through the remote sensing and space technology sensors, I can detect what I cannot see. That means I can use the IR band, radar and other part which doesn't come under my visible spectrum. Then even during the disaster and other where I cannot reach, the remote sensing or the space technology can reach to those places. They can provide information, they can extract information from those places, and they can communicate to us so that I can take my decision sitting here in my room. Now, why this space technology is being so much emphasized? If you see the today's scenario, we are having water stress. And India is one of the states where the water stress has been increasing. It is mostly because of the population, mostly because of the management, but the stress has been increasing. Now let us go. When you talk about space technology, there are two things. One is the sensor-based remote sensing, and the other part is satellite-based transmission. Both comes under the space technology. Now let us come to the sensor-based remote sensing. When we say sensor-based remote sensing, that means we have a spectrum. That's from the part of the spectrum, we can see the visible spectrum, whereas the IR, the infrared, the radar part, the microwave, these part, we being human, we cannot sense, but the instrument can. So we now deploy these instruments in the space so that they can detect and give us the information. I'll give you the example, but before to start with, through remote sensing, we have two types of sensor. One is the passive sensor, one is the active sensors. Active sensors, what we will do, like if you know your camera without a flash is a passive sensor because that light is coming from the sun and this camera is recording the sunlight, which is being reflected from the image. But when you use a flash, that means my camera is giving the light and I am capturing the image. So that is the active sensors. In that way, if we go, now here, if you see, okay, I have the, if you see this part, this is the visible part and this is the near IR. So normally human can see the visible part, but if we talk about the ultraviolet or even if we talk about the microwave or radar part, these we cannot see. Now these are, the sensors are being used to see these parts. Now this is the process how the remote sensing works. For like different objective have a different reflectance to different type of bands. So what we have done, we have put several bands, several sensors in our satellite where they capture a particular band of images. Now the same feature, see these are from the same area but taken in different bands. Now how does the sensor records? It's like it will simply record the reflectance of an object. It is starting from 0 to 255, in total 256. So in the grayscale range, it will simply record the reflectance of an object. Now, suppose a visible spectrum, if you see, we see the water as blue or maybe water as some other color. But if you see the IR band, where whole IR band is being absorbed by the water, so it doesn't get any reflectance. So in IR band, what will be the color of water? It will be black because nothing has come back. But if suppose there is a vegetation, so vegetation, if you see, the vegetation reflects all the IR band. So the sensor will record 255 or the highest value of the reflectance. That means when we project that particular band in a color, we'll see the color. Whereas water we cannot see in that particular band. These are few of the sensors that I am skipping because I am mostly going to the application part. Now we have the spectral resolution. What do we mean by spectral resolution? Better the spectral resolution, we can see the better images. It's like if you see the megapixel of our camera. Previously we had 2 megapixel camera where we used to get the images but they were blurry. But now if you see our camera, they are 48 megapixel, 100 megapixel, so we have a better resolution. Okay? And then when a satellite passes through our Earth, it takes a particular width of the photograph of the particular width. So that width is known as swath. Swath is the area covered when a satellite moves on the orbit. Now, these are examples from a Landsat image. Landsat has almost 7 bands. Now they have again increased to 9 bands, but Landsat has 7 bands. Now these different bands, see, these are from the same area, but you can see the changes in color. So every band has a particular objective, what they will pick up. Now for human, we can see only 3 primary colors: red, green and blue. So all the images, where they have to be projected in these particular colors so that we can see, you human can visualize. Now we very well know from the remote sensing images that blue band is not that used, or that is not much used to our eyes, like for our information. So what we do, because we have three guns to put, like we can see only 3 colors, what we do, we project the green color in blue band, red color in green band, and the IR, which we cannot see but we want to see, that will project in red color. So these are not the actual color, these are the false color, because we have projected green in blue, red in green and the IR in red. So that the image that we see now is a false color composite. It is not the actual color. For example, you see here, this is the true color of an stadium. But when you project the same in false color, that means using the red, green, green, red and IR, here we can see, here this is not, this should be actually green, but it is not green here. This is the astroturf in a football ground. Astroturf is not the real grass. It is a synthetic material. Normally IR, what will do, it will reflect, like that IR band, vegetation will be reflected. But here, because it was turf, so here see, here this part was vegetation, it is projected as red here. These were some vegetation projected as red here, but this is astroturf, so this is not being presented here. So here we can delineate. So these are the capability of different bands. Similarly here, if you see, there was this thermal spring here. Now how do you know that the water body is, like where is the water body? In the visible spectrum we cannot actually see the water body. In the near IR we cannot, like we should have seen, the slight mark is there. This, then in thermal IR band when we see, we can clearly delineate the water body and the structure. So these are the uses that we can play with different bands to take out our information. These all were about the passive sensor. Now coming to the active sensors. What does the active sensors do? It gives its own light or the energy, and then it collects the reflectance. For radar, LiDAR, it uses synthetic aperture and it takes the image. Processing a radar image is very, very tedious task. Although we have projected it very nicely here, but it is very difficult. And similarly the LiDAR normally we do it from a very small distance. Radar is from far. So see, this is the clarity of images that we can take from LiDAR images. Even it has 5 centimeter resolution. So LiDAR are very clear. What are the other uses? Like land surface and elevation mapping. Previously what we used to do, we used to take theodolite and survey area. But with the emerging technology and all, the SRTM, at present it does for 30 meter resolution. Initially it was 90 meter resolution. So we can take a very clear picture of our area, the height, the elevation. Similarly, there are Cartodem from our Cartosat, which has almost 1 meter resolution that we can use. Aster, Global ALS. So I am just giving a brief idea that what remote sensing capabilities are, so that we can use it in our work. Weather forecasting, it is purely a gift of space technology. That when it is going to rain, where the cloud has formed. So these are all blessing of space technology. Land use and land cover mapping. Where the forests are, like we do our classified and unclassified mapping through those where our forests are, where is the cultivation, which area has paddy, which has the other agricultural items. So these things we can find out from land cover and land use mapping. Now let us go to the satellite communication. That was the sensor-based technology. Now we are coming to the communication part. As we were in NHP, we know that wherever we have put a RTDAS, either it is through, like the communication is through INSAT or GSM telemetry, GSM GPRS telemetry. So those data are being sent to the satellite, and then again we are receiving at our base station. So this is how the communication work. Our telephone, these are through the satellite communication. Now, very wrongly we use the word GPS, but GPS is specifically for the US government. We should have used the word GNSS, that is Global Navigation Satellite System. Because initially GPS started, it came in our phone and it was purely on US satellites, but the actual name should be GNSS, Global Navigation Satellite System. Now this Global Navigation Satellite System, what it does, it has many satellites orbiting the Earth. So when we use our phone or any GPS system, it communicates with those satellite and gives us the accurate reading. Now for India, actually previously we used to be, we were using GPS, GNSS, even this Baidu and all we used to use, but now India has its own, but it is specifically for India. It's not in the domain of GNSS. Like we are contributing to GNSS for only the Indian part. Course. This course has been established, part of the course has been established under NHP in many states, and it is also active in Mizoram. Previously, when we used to take our what do we call digital? What is that instrument? When we go to a place that apart from GPS, the high DGPS. Normally, in the previous days, when we used to have DGPS, we used to have two machines, one rover, and one is that standalone system, and another was a rover. But with this advance of technology, what this course network has done, network has established its station where it has been placed, and one can go with simply the rover and take a reading, upload that reading to the Survey of India site, and where they can directly download the exact location of that place, accurate to 5 to 7 centimeter. So initially when we used to go, we used to take GPS reading, where GPS reading used to give us an error from 5 to 7 meters to 100 meters, based on the satellite position. But now, with the DGPS, where initially we used to purchase two machines, DGPS machine, one is rover, one is standalone system. Now we can go only with the rover, take the reading, upload into Survey of India site, and there we can get the exact reading. So now this has reduced many of our rewards. Suppose one is trying to put a water pipeline from one city to the other city. Initially there used to be a theodolite survey where people can go, or even taking a DGPS, they have to survey the whole. Now you don't need it. Simply one can go, take few readings, come back, upload the site, and they can get the exact length of the pipe required, exact length where they should take the pipeline. So these are the advantages of having a course network. Our price has reduced to half, because initially we used to buy two instruments, now we can do only with one instrument. Now coming to the space technology and groundwater. Now this will be specifically to the groundwater, but as I said, we cannot know the groundwater information directly from the satellite images. There are indirect ways. Now these are the major applications on groundwater that we can know about the groundwater exploration site, from where we can take good amount of water. Site for our artificial recharge structure, from where we, in which places we can put our artificial recharge structure. Is there any land subsidence? And these are. So we'll come one by one. Now these are the first order and second order indicator. Indicator means through the features, we can identify. I'll go to the image first, then I think we can better understand. Now, these are the few images. Images, as you said, that black color part, it is water, that we know. So, wherever there is water, surface water, we know that there will be some seepage to the ground and we'll get good groundwater nearby. Now, the other indirect information is that here I am seeing everything is red. Red means vegetation. Near the water body and red. That means this place has some groundwater, or it is rich in groundwater, because of the groundwater only the vegetation has come. So these are the indirect indication. If I want to put a tube well, I won't put it here. I'll put it somewhere here. So these are the indirect way. These are the lineaments. Lineament means fracture and lineaments. So if I have to search for groundwater, I won't go to the places where there is no lineament. I'll go to the places where there are lineaments. Similarly, concentric drainage. So I know that everywhere the water is getting accumulated here. So I'll go there and drill my hole. Again this, along the river, we have good vegetation. So I'll try to find out those areas. So these are the indirect indications. Like for the soft rock formation, like in Mizoram and part of Tripura, it is very difficult to differentiate rock type. But if it is a hard rock terrain, if it is a basaltic terrain, then basalt is dark in color, it will have a low reflectance, whereas granite is very light in color, it will reflect more. So in those way, we can differentiate the rocks. And we know that granites are massive. Basalt, they are massive. But in basalt, they will have traps. They will have fractures. So these are the way that I can indirectly find out my groundwater. Sorry. Now, what are the use of these maps or these images? Based on these images, lineament mapping, I can prepare a groundwater prospect map. And these maps I can circulate to my other offices where they can use this map to find out groundwater. So this is one of the applications. Now, source sustainability of a village. Suppose if I go to a village, I have a map. Now I start marking the lineaments. I start marking the drainage pattern. So I know that how my groundwater is flowing, or even the surface water is flowing. And normally groundwater tends to flow along with the surface water. Wherever there is good surface water, nearby area will be rich in groundwater. Surface water, sometimes what we do, like we cannot directly take surface water and drink it, because we know that there may be some contamination, maybe from the animal, maybe from the other geogenic sources. But groundwater, except for arsenic and fluoride, because these are the, we know that they are geogenic, they are to be treated. But in other part, we can directly drink them. They are reliable. Now this is about the land subsidence study. Land subsidence study, like we have been extracting water. Suppose think about a column which is filled with water and soil. Now when I start removing the water out, slowly the soil will get compressed. The similar situation has happened in parts of Haryana, in parts of Delhi. So in those northern belts, the groundwater is being extracted very rapidly. So that has resulted in the land subsidence. Now how do we know that land subsidence is taking place? Visually we can see that there are some cracks, but how it is affected and how far it can affect, those parts, if I go through the remote sensing techniques, I can predict. This is the part where, this is near Chandigarh area where the study has been carried out. So the reference is there, that which images I have used or our office has used to get this analysis done. So INSAR, this is the synthetic aperture radar of the active sensors. So those active sensors has been used to know that which are the places where the land subsidence has been carried out. And this is the recent study. This is yet to be published, but this is a recent study of Guwahati town, where we wanted to know the change in land use pattern of Guwahati city. So we have our Landsat images. So through Google Earth engine, what we did, we processed all the Landsat images available from the beginning. And see, these are the changes. This is 1985, the land use pattern. Land use pattern means where is the agricultural field, where our buildings are there. So this is land use pattern. No? See how the urbanization has taken place. And if you see the groundwater trend, all are declining. That means with the rapid urbanization, they have been using groundwater, they have been extracting groundwater, and the levels are going down. So these are the indirect uses. Now, in the first presentation, we learned about the GRACE mission. Now, as I said, that groundwater cannot directly be delineated from space technology. Now, this GRACE mission uses the gravitational force of the Earth. It studies the gravitational force of the Earth. Now, we know that when the mass is the same, the gravity remains the same. When the mass changes, the gravity also changes. So, initially, when a recording was done, the GRACE recordings were done. Then, after few years, when again the same readings were done, the changes were found. This is an example from sorry. I will take. So this is the image from 2002 and this is 2014. Now what it does, it simply measures the gravitational force of the Earth, the GRACE satellite mission. Initially, now this is the difference between 2 and 14, and when it was found out, it is the reducing water level. So initially they must have studied that how the reading changes, and with the declining water trend, how it changes. So see, even for India, this northern part, this was published in I think 2016, where there was a huge hue and cry regarding the depletion of groundwater level in the northern part of India. And this is the image that is from Central Groundwater Board. So it clearly matches with the GRACE satellite information. So again, this is also an indirect way where we know that there is a depletion in groundwater. This is how the GRACE satellite works. Again, the same images. These are the Central Groundwater Board. It calculates the resource of India, where we know that this part is overexploited part, and again the GRACE mission also shows the same. Now this is not directly linked with the groundwater, but using the latest technology, altimeter have been placed in satellites where they can measure the actual water level of the flowing river. It simply uses the altimeter height, where today if the flowing the river was flowing around 2 meters above the mean sea level, and if today if it was around 1.8 meter 3 days back, so it will say that okay, there is a rise of 0.2 meters. So these factors, they may not directly affect the groundwater, but we know that higher water level means there will be more recharge. So that's an indirect way. This is about reservoir sedimentation. So this recording has been done since 2005. So 2005 to 2016, it's like the trend. Okay. How the sedimentation has increased. More the sedimentation, there will be less recharge to the groundwater. So normally what we say, always desilt the water body so that there will be more recharge. This is wetland mapping. This is not part of our study, but see, again, our first presenter, he was talking about the snow melt runoff. This was a study done by NRSC, where we know that how the snow cover is declining. With the declining snow cover, there will be less runoff, which will reduce the groundwater recharge, because snow has the best capability of recharging groundwater. Slow melts very slowly, and any slow running water recharges the groundwater. If the river is flowing very rapidly, it won't recharge the groundwater much, but if it is very slowly flowing, it will recharge more. Similarly for the rain, if the rain is of very high intensity, it won't recharge the groundwater. But if the rain is very low intensity and longing for days together, it recharges the groundwater more. This is again from the NHP study that I have taken. They have put 19 sensors through the ground, and through that they are measuring the ET flux. And these 19 stations they have put so as to calibrate the reading from the satellite images. Because satellite images, they give us a reading, and this 19 station they will calibrate. Again, what is the other use of remote sensing? We can do our impact monitoring study. Suppose we put a canal network, and how that canal network is affecting our groundwater system. See, this image is changing. You can see that after putting that canal network, the irrigation has increased, the cultivation or the vegetation has increased. That means that groundwater is getting recharged. So these are some of the method or indirect method that where we can study about groundwater. Thank you. Thank you. Thank you.
Thank you, sir, for a very well explained as well as visually attractive presentation. Thank you, sir. Let us invite to the stage our next presenter, Dr. Sri Krishnan Siva Subramanian of IIT Roorkee. Dr. S. Sri Krishnan holds a Master's in Geosciences from Bharatidasan University, India, and Doctorate of Engineering in Field Engineering for the Environment, Geotechnical Engineering from Hokkaido University, Japan. His research specializes in understanding the mechanisms of shadow landslides and debris flows initiation induced by rainfall and snowmelt. And today, the topic of his presentation is Early Warning System for Landslides through Space-Based Products and Modeling. Sir, you may proceed.
So, thank you. I sincerely thank Irrigation and Water Resource Department of Government of Mizoram for giving me this opportunity, and thank you for the kind introduction. And so far, the first two presentations of today's talk was talking water as a resource. Now I am coming with another argument that the resource can also be a problem if it is abundant with the space and time with respect to its volume. So the water, when it actually abundant within a short period of time and also within a short space, it can lead to problems such as natural hazards, mainly flood. And during the extreme flooding events that take place whenever we have surplus amount of water in our earth surface, there is also secondary hazard that is possible in case of landslides, mainly shallow landslides and debris flows. If we look into the history of over the last decade, in 2013 in Uttarakhand, we may all remember that there was these 2013 North India floods, which have caused widespread landslides and debris flows. In addition, and together with the flash flood that took place, and it has caused more than 6,000 casualties, as well as 6,000 number of landslides across the catchments in Uttarakhand. And in 2018 in Kerala, there was 1 in 100-year flood event that took place because of extreme precipitation, which has also caused shallow landslides and debris flows. And this event actually disrupted the infrastructure as well as the economy of the state in a cascading manner. As you can see, This happened during the Indian summer monsoon time from July to August month of 2018. So there was widespread extreme amount of precipitation that was supplied to the mountainous catchments, due to which we had shallow landslides, flooding that took place all through the months, mainly the peak flow to be happening, which is reaching the dam on like 12th and 15th of August in 2018, and also lots and lots of debris flows. When we have landslides across the catchments, and this material is actually transported to the river through debris flows, and collectively through a cascading kind of mechanism, it has caused the infrastructure disruptions. Similar event also happened last year in Mizoram, this year in Mizoram, not last year, this year in Mizoram, when the cyclone Remal has actually downpoured high amount of precipitation, and few landslide activities happened, because of which we also had recorded casualties in Aizawl region of Mizoram. Very recently, you may all heard about the incidents what happened in Wayanad. It is a rainfall-induced debris flow. Now, people are suspecting that there was also a landslide dam formation, which has caused the second impact, which has caused more than 420 casualties, as well as more than 129 people are still missing. So these are few examples in which the surplus amount of water, though it is a resource given to us by the nature, the surplus amount can also be a problem leading to this disaster. And before going into the space technology thing, so if we look into the scale range of analysis of landslide studies, and let's keep the finer scales here on the left side, and at the larger scale, the landslides are studied from 10 to the power 0 to 10 to the power 4 scale. Why is so? So as I previously mentioned, that more number of landslides are getting triggered in a catchment, close to 6,000. So we need to have studies at this scale, which is mainly based on early warning systems on hydrometeorological thresholds. For that, we need to have the hydrological understanding of the landslides that is taking place. And also we need to have slope scale monitoring for geotechnical thresholds, and we need to understand the mechanisms at finer scale also. At this scale, mainly when we are dealing with 6,000 number of landslides across the catchment, obviously we need to look for remote sensing technology for us to give some idea of the terrain conditions as well as the geomorphology over which the landslides are taking place. Also, there are studies in micro and nano scale, which is actually emerging now, mainly based on biogeotechniques for landslide mechanics. So our work on landslides in IIT Roorkee mainly focus on these scales, and the presentation today will be focusing on this scale, whereas we'll be learning about an early warning system. Mainly the system is actually governed by ISRO. As we have landslide problem here across these scales, it is imperative for us to understand what's happened during a landslide. This is a typical hill slope cross section, a two-dimensional cross section we are seeing. And here we have the geological bedrock, maybe of either of the category of igneous or metamorphic or sedimentary. And here we have the debris cover in which the unsaturated and seepage activity of hydrology takes place. And when we have surplus amount of water, mainly from the extreme precipitation, we do have infiltration exceeded runoff, which goes through the hill slope here. And then we have wetting front that actually penetrates into the soil surface, which leads to saturation, and this material can fail, which we call it a shallow landslide. And when this material actually get together with abundant amount of runoff, it converts into debris flow, then it meets the rivers and trigger as a flash flood. With this schematic, so this is happening on a slope scale, on one slope. As I already mentioned, more number of landslides are happening on an event of rainfall. So we do have early warning systems across the global scale. These are the countries which use the intensity and duration of rainfall to give the early warning of landslides. And also a few other countries which use a complex threshold. We do have a system of ISRO here, India, which is still experimental. And the current presentation which we will talk about is some improvements what we have done for this system. So this ISRO's experimental landslide early warning system is mainly based on the space-based products that give information about the terrain, and this is actually implemented in Uttarakhand state along only few road corridors, not across the entire state. This system actually gets the forecasted rainfall information of intensity and duration, and they do have a database of existing landslide which has happened because of the rainfall, and a simplistic threshold line is drawn, and if the intensity and duration of the forecasted rainfall will exceed this line, which means that the landslide is going to happen. If it doesn't exceed this line, which means that the landslide may not happen. That's a simple criteria. But the problem what we have with the ISRO's existing system is, as you can see, the number of input points are very small, okay, which means the historical database which gives us the information of the rainfall intensity and duration has recorded only few number of landslide, mainly less than 100. So with this less number of landslide, it is always difficult to rely this will be the exact intensity and duration threshold of landslide for which the warning can be given. An alternative approach which IIT Roorkee is currently working on is to enhance the number of observational points here through a modeling framework which we have done, and this has some mathematics and hydrological components which I will not detail now, and through which what we are doing is we actually review the existing inventories of landslide, and what you are seeing here is the fieldwork which we have done in the Kedarnath catchment in Uttarakhand, through which we actually run our model for one catchment, and we are actually improvising the existing observational points of landslides based on pure hydrological as well as geotechnical modeling. And once we do it, we actually have comparison of intensity and duration thresholds with the existing studies. So for which what you are seeing is the case example, still 10 years behind today. We are still working on the 2013 landslide events to improvise the thresholds. And these are the landslides that actually got triggered during the 2013 North India floods. What you see here are landslide polygons, and 120 of them are debris flows, which means it happened along with the flooding event that took place in 2013, especially in June 2013. And all these debris flows were mapped by ISRO, NRSC, National Remote Sensing Center, and they have actually given us this inventory. What we have to do is, we have to find the hydrological condition in which these landslide has got triggered. So we have made a framework to actually know the intensity and duration thresholds of the landslides of all the 120 polygons under which the landslide have occurred, so that if there is an event of such extreme rainfall in the Kedarnath area again, so this intensity and duration threshold can help us to give an early warning or at least the forecast. So we have relied on an atmospheric numerical model, that is the weather research and forecast numerical model, to get the intensity and duration of rainfall. This is the comparison of the rainfall data from the satellite derived rainfall data, through which we have got the intensity and duration curve, and this is the debris flow volume which got generated from our model, and this is the empirical calculation of the debris flow volume. As you can see here, still there is a much lag in the overlap of the landslides occurred in 2013 as well as the debris flows that actually simulated from our model. With this, we actually got this curve, as you can see here, the intensity and duration curve, which based on our model, we believe this might have triggered the debris flows in the past. And once we compare this curve with the existing curves of the similar catchments in Uttarakhand, we found our curve to be sitting on this plane, and through which we are actually adding more points to the ISRO's existing experimental early warning system for landslides, and we are actually enriching this curve. But still this is not enough, as we understand that the response of a hill slope when a landslide happens or a flash flood happens, it actually governed by the moisture conditions of the terrain, that is the hydrological conditions of the terrain. Whereas this threshold, this intensity and duration threshold, it actually a meteorological threshold, not a hydrological threshold. So we have to advance this into a hydrometeorological threshold, respecting the water which is actually existing in the terrain, for which we look into the early warning system which is actually operational in Japan. So that is known as soil water index, much informative to hydrologists as well. In earlier 1970s and 80s in Japan, even the flood forecasting was done using soil water index, where the hydrologists there, they have got a very good discharge curve through the soil water index model with the observed data. So this model, what it calculates is, based on hourly rainfall, it calculates the soil water index based on a formula. It is a tank model, and when this line exceeds this line, then they think that a landslide or a debris flow, or they even call it as sediment disaster, it is possible to happen. And based on which they give the early warning information for landslides. Earlier, like I did my PhD from Japan, I also worked in this system at that time. Earlier they were working on a 5 kilometer by 5 kilometer grid for giving the landslide early warning. Now they have improved up to 1 kilometer by 1 kilometer grid. Whereas in India, we are still restricted to have our early warning only with the road corridors still now. And when we put this system, means this threshold, into our existing early warning system of ISRO of NRSC, so we do see that for the 2013 landslides that happened in the Kedarnath catchment, this criteria, it's actually fine, which the soil water index is actually exceeding the critical line. But this is actually for 12.5 kilometer resolution of the data set. This is the Uttarakhand state, what we see here. And this also works for, you can see, this is an animation from 15 to 17 June 2013, in which the landslides were simulated. So you can see some high amount of rainfall to be happening at the point where the Kedarnath catchment here, so you can see. So we have actually tested the Japan's early warning system within the framework of ISRO, whereas the landslide early warning system is based on space products, but actual warning is not given based on space products. It is actually given from the intensity and duration of rainfall. And this improvised system actually tends to work better for the ISROs, only for the case of Kedarnath, which we have simulated now. And this is actually currently being expanded to other catchments of Uttarakhand and then to the entire Uttarakhand state. That's the objective of the project. So, if I summarize, sorry about this. For an early warning system of rainfall-induced landslide, the much attention to be given, means I'm an engineering geologist, but much attention to be given to the treatment of water that many hydrologists will also agree to. And if we can quantify the amount of water that will be received at a certain space and time, then it is easy for us to give early warning for both sediment disasters such as shallow landslides and debris flow. So I think I kind of run quickly with my presentation. I think the audience will be happy about this. But one thing, before I conclude my talk, so this is a recent article in New Indian Express. So how Aizawl system could serve as a model for Kerala. Okay. So the Aizawl Municipal Corporation, I also got to know about this like 2 years before. They have done a very good 1:5,000 scale landslide susceptibility mapping for the Aizawl system, in which they have the guidelines of where to make the building and where not to make the building. And this article, which has published recently in this New Indian Express, states that for Kerala, in which the recent Wayanad disaster had taken place and has actually caused close to 400 fatalities, and this model can be taken as a reference in which we can actually give guidelines for where to make buildings and infrastructure and where not to make. Provided this, even if we have a very good guidelines of where to make our buildings, the early warning system is important, where the hydrometeorological threshold should be considered properly for a proper early warning. So with this, I thank you all for this opportunity, and I'm open to some questions and discussions as well. Thank you very much.
Thank you, sir, for your brief yet very precise presentation. Thank you for the brilliant presentation. Questions will be raised by the panelists in the afternoon session.
Okay.
Right. Thank you, sir. Now let us invite to the stage our next presenter, Professor Arnab Bandyopadhyay of Northeastern Regional Institute of Science and Technology, NERIST. Dr. Arnab Bandyopadhyay is a professor at NARIS, specializing in hydrological modeling and remote sensing in water resources. With a strong administrative background, he has held various positions within NIH and NARIST, including controller of examinations at NARIST. Dr. Bandyopadhyay has served on committees as an external expert at universities and as a reviewer for prestigious journals in hydrology, agriculture, and environmental science. He is also a member of various professional bodies such as Indian Society of Agricultural Engineers and International Association of Hydro-Environment Engineering and Research. And today, his topic will be flood warning system of Klong River. Sir, you may proceed.
What do we select? Extend. That's what I mean. Extend. No. You can just go to the second screen only. I don't need this. Okay. Just a second. Let me take it here. Where is it? It's not working. Yeah. Sorry about that. So, good afternoon. And I am the last obstruction that you have to overcome to reach your lunch. So, I'll be presenting on a flood warning system that we have been developing for Klong River Basin for last 2 years. And I'll also tell you, it should not have ideally taken 2 years, but why it is taking a little longer than we expected, that also I will tell you. Sorry, sir. This needs to be changed. Oops.
May I please request the technical staff to assist him?
That is already selected. Actually, the problem is the primary display is that one, and this one is the secondary display. That's why it is happening. I think this will solve it. it's working? Yeah. Okay. So, it is still the same. So I discard PPT and I come to PDF. And I will tell you why this took a little longer than we expected. And this is today's presentation outline. I'll first tell you the problem. Of course, most of you already know that. You are experiencing it firsthand. And then how we are trying to address the problem, because we cannot solve the problem. Rather, having a little bit early information about it is going to happen can reduce the damage. So that's what we have thought of, and then we are taking a two-step approach on this. One is a very short-term forecast based on upstream gauge level, and second is a medium-term forecast based on based on weather forecast or numerical weather predictions. So this is the problem statement. As you can see, almost every year during monsoon, during the months of May to August, we are facing this. 2017 is there, 18 is there, 19 is there, 20 is there, probably 21 we did not face that kind of a severe flood here. Then 22, 23, and very recently on 28th May 2024 also, we faced this. And I have just taken these clips from those websites of national news portals. So here we propose a development of a flood forecasting system for the Tlang River Basin, which is dependent on the RT dash. It's unfortunate that the RT dash system will be explained after the post-lunch session. It would have been easier for me if it was before. Anyway, let me try. And then we want to develop, operationalize and demonstrate a sophisticated water level forecast and flood warning model, which is specifically tailored for Tlang River Basin. And that's the gauge to gauge correlation or short term. But also as a parallel solution, we are also developing a medium term forecast, which is based on a hydrologic modeling, a GA based rating curve, and also cost distance analysis, so that we know beforehand, maybe a couple of weeks before the actual date, that there is a strong chance a flood may be coming. So you are prepared, and then when it is supported maybe 1 day or even 6 hours ahead that now the flood is coming, it will be easier for people to relocate and reduce the damages. So that's what the two-step approach that we are having. One is to develop a short-term flood warning system based on gauge-to-gauge correlation and rainfall-to-water level correlation using machine learning. And the second one is to develop a medium-term flood forecasting and warning system based on hydrologic modeling and numerical weather predictions. So this is the study area. You know better than me about this, so I don't want to explain this. I may be wrong sometimes. And then this is some preliminary survey works that we have done. First, to select the warning sites. For example, we have 4 audio warning sites, 4 audio-visual warning sites, and the entire system is fed by 8 AWLR sites for the short-term forecast project. And here, the sites were selected based on past experiences where we had floods in the past, where the maximum damages happened. Also based on proximity of the villages to the river, and people's tendency to go to the near to the river, or maybe crossing the river sometimes. So based on these factors, these sites were selected. And also we conducted some ADCP surveys to develop to calibrate rather our rating curves further. I will come to the results of this. And so this is the framework. we started with these CWC gauge stations. CWC has a good coverage of discharge stations on the Tlong River. And then this is the main Tlong River, and it has two major tributaries. One is Tut and another is Teire. So all of them, they join together before the final outlet is at Bhairavi. Then it goes to Assam in the north. And these are the meteorological stations that we have. Mostly the meteorological stations are on the boundary of the basin, and sometimes outside also. Very few are there inside the basin, but still they are good enough for our purpose. And then these are our warning sites, as you can see. And now I have also placed the AWLRs, that's RTDS AWLRs locations. So these squares are RTDS AWLRs, and the green ones are currently sending us data, whereas the red ones are currently not working. And then our warning sites, we have three clusters primarily. One is here, and if you look at the enlarged image of the cluster, then we have two audio warning signs and two audio visual warning sites. And then here there is a second cluster where we have two audio warning sites. And then near Bhairavi, here we have, this is also Bhairavi River Crossing 1 and Bhairavi River Crossing 2. And then here at the outlet also we have one audio visual sites. So this is the instrumental framework of the work. Now we come to the short-term flood forecasting. So here we are using machine learning models to train and then to forecast. And here we have used three algorithms: random forest, linear regression, and LSTM. And it's just like all other machine learning approaches, we have tried to build our model based on a 70-30 ratio. We tried other proportions also. This one gave us the best result. And then the hyperparameters were tuned, and then we selected the best ML model, and then we have the short term with water level forecast at the downstream station. Now, while we were developing, that time we faced the challenge of data, because that time only two stations were working. One is Shimui and the other is Bhairavi. So we have taken Shimui as the upstream station and Bhairavi as the downstream station, but there were again the past data records that we have got, they were not synchronized. Some data we had from Shimui, some data we had from Bhairavi, but they are not of same periods. Very limited overlapping data we got. So with which we started to develop our model, and then the problem is we are trying to forecast the water level at the downstream based on the water level at the upstream. And if the upstream water level is not feeding me real-time data, then how do I forecast? So that is why I had an additional challenge to solve here. So that's why we started first single station forecasting for Shimui, because Shimui had a time series. Then we started forecasting upstream gauge first, and then based on that forecast we started forecasting for the downstream, and we got a very good result for this single station forecast for Shimui, and which was almost a perfect prediction. And then with this we went to the downstream, and in the downstream we also got a good kind of result, because our challenge was, the objective of it was to give a prediction accuracy of less than 30 centimeter. So we got a prediction accuracy of about 23 centimeter, but still I am not very satisfied with this. LSTM is supposed to give better results, and this is again where you can see that the water level is not that much varying. It is kind of same or slowly changing, gradually varying. What will happen when the water level is rapidly varying, when it is a kind of flash flood, then that is yet to be seen, and we will probably see it very soon, because that hurdle that we had is now almost overcome. I'll come to that. And then we also tried a linear regression model, which is unlike LSTM. The linear regression model also gave us a very good kind of match. So we thought that maybe we can keep this in the model, because this is also, it's a very simple thing. not as sophisticated as LSTM, but still it may give us a good result. So ultimately, when we go ahead, we have to have upstream data as well as downstream data as a training data set, along with the date and time for the data. And after that, when the prediction comes, we have data. Based on this upstream data, the downstream prediction will occur. Now coming to the problem. The problem is, we are supposed to have water level data coming in hourly from 8 stations. Now when we finished our model based on 2 stations, then I was very happy to hear from Hamlet sir that now the stations are ready and I can access my data. I went to access the data from the server and I found that out of 8, only 3 sites are giving data. When inquired back to the vendor said, sir, I will send my team tomorrow to the sites and see why the data is not coming. And next day he reported that, sir, we installed there, and unfortunately most of those sites don't have a mobile network. So obviously GPRS modem based data transmission is not having mobile network, but the mobile network is not very dependable. Sometimes it is there, sometimes it is not there, so it is a failure. Then we look for alternative solution, and the solution was already given to us by sir, that INSAT based. And then in June this year, we tried to see if the INSAT data is having feeds from all these 8 stations. But unfortunately on 18th of June, INSAT data was stopped throughout the country because of some major upgrade in the system. And now I am very happy to announce that from 1st of August, or rather 31st of July, the data have started coming in, and we are also receiving INSAT data from these sites. But again, sir, out of 8, we are receiving data from only 5 sites. I'll show you. Before that, so this is the very simple GUI kind of thing that we have developed for the user, because they don't need to go to the details of the models and etc. It's just need to select the algorithm and click simulate, and that will give the prediction. However, when it is deployed in the system, that time it will be fully automated and it will give you warning based on 3 levels that user defines: yellow, orange and red, what kind of flood is expected, and based on that the audio and video warnings will be given. Now this is the thing I was talking about. So we have 3 clusters to forecast. One, all the 2 audio and 2 visual warning sites are here. So they will work on based on a model which is trained with these 3 upstream gauges and 1 downstream gauge, which is here itself. So whenever we train the model with these 3 upstream gauges and this downstream gauge, and then whenever we have high water levels in these 3 upstream gauges, this will give us a forecast, and based on the level of the water level forecasted, we will issue warning, either both audio and visual, based on the severity of the flood that is expected, whether it is yellow, orange or red. Here, out of the 3, this Aizawl Roorkee, this site is not feeding us data, but still we have started working with the remaining 3. This is not that much of a problem. Similarly, with this Bhairavi, which is the main outlet, here also we plan to have all the 7 gauges above it upstream, and this was our downstream. And for forecasting Bhairavi Chimbeng and Bhairavi Marveng, here both the sites are here, so we planned this way. But here out of 7, again all these 3 upstream, they are not giving us data, but still with the remaining 4 upstream gauges and these downstream gauges, we have started working on this cluster as well. But our main problem is with this second cluster, where we have 2 crossing sites which are very important flood prediction points, because people tend to cross the river here, and we have 2 warning sites here, but the main target downstream site based on which we will give forecast, that is not giving us data. So at least this should work, Baichali and Sairang. So once this works, we will have a very effective flood advanced early warning system based on gauge to gauge relations. I am also exploring the idea of putting the rain gauges as the input nodes, so that probably that will be helping us in improving our accuracy. The second one was a physics based medium term flood forecasting, where we have set up a hydrological model, and it was mandated that we should not use any licensed model. So we have selected HEC HMS. Probably our previous speaker mentioned about HEC RAS and SWAT. HEC RAS was not suitable in this case because that's a hydraulic modeling system, and we don't have much input to give it the river cross sections. Secondly, the SWAT model that was used, that was discussed, when we compared, we found that HEC HMS is much better at predicting the peaks than SWAT. SWAT is good for event based models, even sometimes continuous models, but HEC HMS, when we use soil moisture accounting for losses, it gives us very good prediction on the peaks. So that is why, because it's a flood model, we selected this. And then, so from this calibrated and validated HEC HMS model, when we feed this with the medium term forecasted numerical weather predictions, it gives us the discharges. From the discharges, then we give those discharges as input to the second model, which is a GA based rating curve, and which converts those discharges into water levels. That's how we have bypassed the requirement of a hydraulic model. Hydraulic model will directly give you water level. We are getting discharges from this hydrologic model, and then we are feeding it to the rating curve to get the water level. Next, then we have developed a cost distance tool on a GIS platform, where this water level, when put into the DEM or digital elevation model of the area, will also give you the extent of the flooding, how much area it's going to be flooded. So by utilizing all these three things one after another, we have achieved the purpose or output of a hydraulic model without going into the data requirement of a hydraulic model. So in the HEC HMS model, we are using soil moisture accounting for losses, as I already said, to transform from the excess rainfall to the discharge. We are using Clark unit hydrograph. Base flow is taken care by a linear reservoir. Evapotranspiration is by Hargreaves, and routing is by Muskingum. So that is how we are getting those discharges. And then this is the calibration and validation of the HEC HMS model. And then those discharges are feeding into a GA based rating curve. Here also we have tried to develop rating curve based on least square fitting, based on exponential curve fitting, and based on genetic algorithm. Genetic algorithm gave us the best result, so we have selected that as a final rating curve generation tool. And then, so these are the results obtained from those three approaches that we have tried for developing the rating curves. So this rating curve, GA based rating curve, it converts the discharges from HEC HMS to the water level. And lastly, those water levels are then put into a digital elevation model of the area, where we identify the river course on the DEM. So this is the river, and suppose based on the HEC HMS simulation and the water level from the rating curve, we get that the river height is 91 meter. So then the cost distance analysis will tell you which of the grids will be flooded. So for example, the river height here is 91 meter. So of course from here, this 90 meter grid will be flooded, this 90 meter grid will be flooded, this 91 will be flooded, this 90 will be flooded, this 91 will be flooded. But wherever we have discontinuity, then even if the DEM grid is lower than the river water, it will not flood. And if it is higher than it, then of course it will be not flooding. So based on that, we convert this to a binary grid, where the 0 means it is flooded and 1 means it is not flooded. So by this we can also generate the extent of flooding. So we have tested this approach based on 2 points that we have from high floods of 2018 and 2019, probably 18 and 19, right? And then this is the flood point of 14th August 2018 or 14th June, sorry, 14th June 2018. This is the flood point, and as we can see that the blue layer is our physics-based 3-step approach inundation, and this is the flood mark. So we are pretty close. It's just 9 meters away from the flood mark. Whereas if I go by Sentinel, the Sentinel-2 SAR, that is giving us even 9.56 meter inaccuracy. So we are pretty close to satellite-based assessment of inundation. But the problem with satellite-based assessment is that in satellite we can only post-analyze where the damage has already happened, whereas in our model we can forecast that this is going to be the flood extent. So that is how we are trying to overcome the challenges that we have. But when we go to which medium-term weather forecast that we use, we have tried 3 models. One is the NCM RWF, which is a very much Indian product. Then we have European Center for Medium Range Weather Forecast, and then we also have NCEP. These are not Indian product, but they are providing forecast globally. And as of now, we have found that European Center for Medium Range Weather Forecast is based for Thlong Basin, accuracy wise. So we are right now doing it with this. If other products improve their accuracy, then we can any day shift to that. That's not a problem. So you might be thinking that this is a misfit for today's topic, which is emerging space technology applications, but the missing link is the INSAT. So whatever is happening in the ground, we are sending to INSAT, and then from the INSAT we are getting real-time data based on which the forecast is available. So without that, it was not possible. Thank you.
Thank you so much, sir, for the relevant and much needed for the state presentation. We shall now have our lunch break, and once again I request all the audiences to follow the ushers when going out for lunch, and all of us are requested to come back at 1:45 p.m. sharp so that we can continue the session. Thank you. Hello? Hello? Students who are still outside the hall, please come in. And all other audiences are also requested to come in. We shall start with Pona la om te kha khongain in lo lu thei to chuan session kan tran le don to e. Presenters, audiences are requested to come inside the hall. We shall resume our DAMC, New Delhi. Sir holds a postgraduate degree in applied geology, remote sensing and hydrology from the prestigious universities in India, including IIT Roorkee. With 28 years of experience in water resources, GIS and remote sensing, he focuses on GIS-based modeling of surface and groundwater resources. Sir Nair is a team builder, trainer, and has received recognition from UNESCO for his work on digital groundwater user maps and rejuvenation of dried rivers. Sir, the stage is yours.
Thank you so much. Good afternoon, and immediately after the lunch, you maybe feel a little bit sleepy, so I will try to be as brief as possible, and let us start. And I would like to thank you, WRD, for giving this opportunity to interact with you all, especially interacting with the youngsters and students is very enlightening, and happy to do that. I am being a trainer. My presentation will be little bit detail oriented, where little bit on a student point of view, on a trainer point of view, how things will work. That is what I am really focusing. Let us start from here. And my presentation topic is erosion potential of river basins using spaceborne data. My presentation I summarized into soil erosion concepts, how data can be acquired, and what are the software we need to have to process this data, and what is the methodologies available, and what are the factors for the soil erosion to quantification of the soil erosion, and how to derive a soil erosion potential of a basin, and how we will delineate this, divide the catchments into sub-catchments or micro watersheds, and how to categorize based on the erosion potential, how to categorize and prioritize our micro watersheds, and what are the control measures available to prevent soil erosion. And soil erosion is a silent disaster. It is always happening with every rain, every spell of rain, some amount of soil erosion happening. It is a silent disaster. It is happening silently and without our knowledge actually. And around 130 million hectares of land is affected by soil erosion every year in India itself. And this soil erosion is mainly depending on the rainfall intensity, soil erodibility, how we are using our land, and slope of the terrain. And now to quantify the soil erosion, we need an algorithm or we need a formula. Revised universal soil loss equation is a best formula which can be applied with the help of spaceborne data, so that data can be acquired through will be available easily, and there is a robust algorithm to process the data, and it can be processed in a GIS platform also. We don't need to manually do much work. That is the benefit of this method. And per se we need rainfall data for this purpose. We need definitely soil type and digital elevation models we require, land use, land cover data we require. We need a certain processing softwares like ArcGIS, we can be replaced it with the QGIS also, which is an open source software. And then for some of these specialized analysis, Saga GIS will be more helpful, and Global Mapper can also be used for delineation of micro watersheds and all. So Global Mapper also can be used, but one of the software alone will also serve the purpose. And this is the overall methodology for quantification of the soil erosion. From the DEM we will get the flow direction and the slope of the area, so that we can determine the slope length factor. From the rainfall data we can create the R factor of this formula, and from the soil data we will get the K factor, and land use, land cover, C and P factor can be obtained. So combining all this in a GIS software, we can create the erosion potential, and later we can do some statistics analysis, and we can come to the prioritization of the micro watersheds. And on a student point of view, I prepare this presentation. And for a student, unlike government offices or when we are doing a project, being a government office, government related projects, we will get easily data, people will provide data. But when a student starts a project, there is a question as to from where I will get the data, because the data most of the data are not freely available. But some of the data is freely available, and these data are proven is a data source. NRSC has developed a site Proven, where most of the relevant natural resources data is there, not only digital elevation model, some of the other land use, land cover, some of the Cartosat product, all those data are available, drainage network is available, basin boundaries are available, and this is a free data source where whenever you want a data, you can freely approach this site, and most of the Indian data will be available here. And how to first we need for the delineation of a basin, river basin, we need a digital elevation model. Otherwise, from the Survey of India topo sheet, it will be a tedious process because initially we don't have any river network or anything to start with. So TEM definitely we require digital elevation models, we require. This is the process in which we derive. We need a rough idea of the latitude, longitude of the area. With the help of that, in the Bhuvan side, we can put that. This is the latitude boundaries and this is the longitude boundaries for me. Then that tiles will be selected and it can be easily downloaded. Once it is downloaded, it need to be mosaiced in a software, and we can get the final software. We can put our own this boundary here, and we can clip the data for our area. This way we can obtain the digital elevation model. Once we have the digital elevation model, for delineating a watershed, we require certain process. We may have initially the raw digital elevation model. We need to process the sink and fill. Certain failure areas will be there due to cloud cover and some other reasons. When the satellite is processing the data, some failure areas will be there. We need to make a little bit rectifications of the data. Once we done that, then another step is the flow accumulation, and all these processes possible in ArcGIS software. Then it will convert it into a flow direction raster data. Once we have the flow direction, it will accumulate it into a stream network, and after getting the stream network, if we put any point anywhere in the data, we will get a basin boundary based on the point which we have given. In this case, you can see that I have put a point here, so that my basin will be derived out of this drainage network. In this way, we can create the river basins. Once we have the river basin, okay, we have the boundary with us. Now all the factors we need to create. First of all, how to create the R factor. R factor is the rainfall factor. Basic data is rainfall. Again, question arises from where we will get the rainfall. So rainfall we can get it from the IMD website. It's a 0.25 degree by 0.25 degree data is the grid data is available. For converting the data into a usable Excel format, we may require a Python console or a Fortran code or a C code or some programming we need to do. Some of the free softwares are also available in the IMD site itself, where we can convert this data into an Excel format. Then only we can use this data. And we need rainfall data. For getting the R factor, we need the rainfall data and the catchment boundary. Once we have the catchment rainfall data, daily data will be converted into an annual data. Here you can see that all the latitude, longitude values are there. For various years, rainfall values were there. This we already totaled. Initially, it will be a daily rainfall data. This can be converted into annual rainfall data. Once we have the latitude, longitude, and all the annual data will be averaged to get the average of 30 years. And once we have the latitude, longitude values, we will get a maps like that for a whole India. It's a one-time process. Once we process it and keep it with us, anytime we can reuse it for any area in India. And once we have this data, this is our study area. But the problem again, as a student or as a trainer, many of time practically when we are doing things, we have only two grids available. This is not sufficient enough to process the data and get the R factor. So we need to create a buffer of our area, slightly larger area we need to process. Once we process a larger area, we have many grid values are there. Once we have the grid values, we need to select by location. There is a tool, all the grid values we can select, and that is segregated. This is our wanted data from the whole India data. Once we have the data through IDW or any of the statistical method like a Kriging or any of the statistical method, we can extrapolate it into a map form so that we will get the rainfall distribution. This, and then based on our area we can clip the data and we got a rainfall distribution. Once we have the rainfall distribution in a raster calculator, initially I have told you that how to convert the rainfall into R factor based on an algorithm. In raster calculator we can convert it into R factor. So we got the one of the factor for the universal soil loss equation. Now the next factor is K factor. K factor is a soil erodibility factor, how easily soil can be eroded. Certain soil easily erodible, certain soil like sticky clay may not be easily erodible based on its characteristics and texture. So if you have a detailed soil map, it will be always good, but most of the time we may not having. So FAO is having, Food and Agricultural Organization is having a standard soil map for the entire world, and for the India portion we can always take out that, in which our study area may be falling in a small area which we need to clip and use. Once we have the data, and initially we have only one, in the legend only one number will be there, that number will be converted into there is another legend along with it. Using this legend we know that it is an alphisol, it is a luvisol, or what kind of soil it is. Once we have the information of what kind of soil and what is the texture of it, both the data is available in the attribute part of this table, we get a soil class. Once we have the soil class, it can be converted into K values, and we can have our K factor. So this way FAO soil data we will convert it into K factor. Now the LS factor, again digital elevation model we require. Through formula we can create this. This is the formula for that, and in this slope is always given in percentage, and this constant is taken as a 22.1, and NN is the value based on the slope percentage. If these are the slope percent, NN value will be this. If we substitute these values in this formula, LS factor can be created. And this is the entire process involved in that. We will get initially the raw DEM, then we will do the calculations, as I said earlier, we will fill the sinks and correct the DEM. Then we will make the slope analysis and we will get the slope, and then we will analyze for the length, and ultimately we will compute a slope length factor. And in practically, this is the way in which a LS factor will be created. Initially it will be a raw DEM, it is a filled DEM, it is a slope map will be created here, and ultimately LS factor will be created. This will be the values for the LS factor. What we are doing, every spatial data we are converting it into a digital numbered data, raster data, so that we can easily compute erosion potential. And next factors are C and P factors. C is a crop vegetation factor based on the land use land cover. For example, forest, if the forest is the land use land cover, then it will protect your soil, and if agricultural is happening, more soil erosion is possible. And suppose some road constructions are there, more erosion is possible. Based on your land use, the C values will change. Similarly, P is a protective factor. Forest will always protect the resist the soil erosion, and some other activities will enhance the soil erosion. These factors are based on the land use land cover. Now, obtaining the land use land cover, there are many sources. FAO land use land cover is there, Sentinel land use land cover is there, NRC land use land cover is there, based on our scale. And if we can create our own land use, once we have the satellite image, we can do the supervised and unsupervised classification over it, using various field verification, we can get the land use land cover. For example, I am keeping the Sentinel data where land use land cover can be derived, because it is a 10-meter resolution derived data. And this is the process involved in the CNP calculator. We will download the data here, then we will cut the land use land cover for our own area. Then initially it will be a raster data, it will be converted into vector data for our easy editing. Then we will club all the categories into, and we will convert this legend into our sensible land use land cover classes. Then we will assign values here. In the attribute table, we will assign values. How we will assign values? These are the standard tables available for that. If it is agriculture, it is 0.5. If it is plantation, it is 0.02. Here it is for the P factor. If it is agriculture, this is the value. If for forest cover, 1. These are the values available. This we will apply, and we will get the, and then we will again convert it into raster format by taking C as the factor and P as factor, so that 2 layers we will be there, so that all layers we have. This is the R factor we created. This is the K factor we created from the soil data. This is the LS factor we created from the digital elevation models. This is the C factor which we derived from the land use land cover. This is the P factor we derived from the land use land cover again. Once we have these layers, by combining all these layers in a multiplicative model, in a raster calculator, we can calculate the erosion potential. Once we have this is the erosion potential map of the area, and once we have this, we can put our micro watersheds. Main watershed can be divided into micro watershed using global software, global mapper it is possible, or SWAT model initial DM processing that element there we will get easily, that is an easy way of getting micro watershed. So we can divide micro watershed into number of our major basin into micro watersheds. Then after this running a zonal statistics for each micro watershed, we will get the values. This is the area and this is the sum of the erosion potential we have. And once we the data is in the tabular format, we can do some statistics on it, so that we can classify the area into severe to severe, very high soil erodibility, medium, slight. So the information which we get from here, just suppose I need to prevent soil erosion. Instead of going to the entire area, I can initially go to my priority area. Here I will do the major activities. So rest of the area I don't need to touch upon, and especially on the slight areas I don't need to look into, because there already soil is stable. But these vulnerable areas are this area. Instead of investing my money into the entire basin, I can concentrate into few micro watershed where my erodibility is very high. That is the benefit of this study. And once we have this priority area, we have certain methods to control the software. Nalaband is one such area where it is locally available material. We will close, we may make a kind of check dam over here, so that water will easily pass through and sediments will be stopped. So this is one of the method. This is a structural intervention, and in the basin in priority area, both the structural as well as the non-structural measures are possible. This is a structural method. Another structural method is check dams. Check dams again it is a slightly higher level of Nalaband, and here again the height of the dam will be around 2 meters. And more water will be passed through it, so that we are not blocking water, and at the same time we are preventing sediment in the upper reaches itself. Then another method is tow walls and retention walls. Here in Mizoram, almost everybody may be knowing all these retention wall and this tow walls and all. I am not going much into it. And terraced cultivations, being a hilly state, it is already prevalent here also. Terraced cultivation, this is a trap ponds. Actually it is for the nutrients, and both for the nutrients and sediments. And
from the agricultural fields, when the flow is there, it will be trapped in a small linear ponds, so that in the other times the silt will be reused in the farm itself, so that our nutrients will not be flow away from the area, as well as the sediment will also be trapped. So this is also one of the good method. And another is the gabion structure. Gabion structure, where boulders are placed inside the network of a iron net, so that rocks will not flow away by the water, so that the sediment will be stopped and the water will be easily passed through. These are the gabion structures. Now some of the nature-based solutions are the afforestation. And while doing the afforestation, we should not go into plantation where local trees which are not adaptable to the local environmental conditions. Actually, we need to collect a palette of seeds from the local plants and make saplings of the local plants and plant over the area, so that another 3 years we need to protect also, we need to give watering also. After 3 years, trees will sustain itself and it will become a forest. So and there are several methods, Miyawaki forest methods, and there are several methods to do it. When we are really, somebody is interested into, they can go into the details of how to do this. This is afforestation is one. Napier grass is commonly used in India. It is having some uses. The grass is having some uses, and it is prevalent to control the soil erosion. And being a hilly state, this kind of things need to adopted in Mizoram as well. And this is a grazed waterway. Waterways are planted with certain grasses, so that flow velocity will be checked. Sediments will also be blocked. Sheet flow will continue, so that water will flow and sediment can be prevented in reaching the major streams. This is my presentation.
Thank you very much, sir, for sharing us your valuable knowledge with us. Questions will be asked by the panelists in the later session. Right. Thank you very much. It was a very important presentation, which can be very useful for our state, Mizoram, as well. Thank you very much, sir. Now, proceed to the next presenter. Let us call to the stage Mr. Ranjit Das, scientist and engineer from Northeastern Space Application Center, NESAC, Shillong. While he is approaching the stage, Mr. Ranjit Das is a scientist and engineer at the Northeastern Space Application Center, Shillong, with a background in water resources engineering. He has been working in the Department of Space since 2004, focusing on water resources, watershed, and disaster management. With 20 years of experience in applying space technology in these fields, he has led various national and regional projects funded by government departments as well as PSUs. If you are ready, sir, the floor is all yours.
Thank you. Good afternoon, everybody. So, I am planning to speak something on space and geospatial technology applications for water resources development and management in Northeastern region. By now, most of the speaker has gone through the very basics of remote sensing. Even the sensors available here also been shown, and their direct applications also been listed. It is there. So it was said. But okay, still I will talk slightly case specific, and maybe it will be a different. So if I say space technology has been used for the management and development of all natural resources, it is also being used for water resource management and development. But we know, even though 2/3 of the Earth's surface is covered by water, but fresh water is only 3%, and out of which only 0.3% of water is available as a surface water, which is not even well distributed. If it is there, if it is somewhere more, it is somewhere less. And well, it is not well distributed, same time it is not distributed over the time. It is more in the rainy season, it is dry in the wet season. So this is where management lies. Therefore, proper management of water resources is very crucial. The water resource management involves the process of planning, developing and managing water resources to ensure adequate water quantity and quality for various uses, which will benefit both human and ecosystem. Different components of water resources are institution, infrastructure, incentives and information system that support and guides water management and uses. And there are some practices which are sustainable. So we have to go for sustainable management practices. Different organizations are involved. They are government agencies and local authorities responsible for creating and enforcing water policies, regulations and standards. Likely, environmental protection agencies and water resource boards, organizations that implement and oversees water management practices such as water utilities, river basin organization, and irrigation management committees, etc. The major challenges to water resource management are rapid population growth. The population growth induces water stresses and water pollution. The rapid increase in population leads to an increase in water demand for domestic, agricultural, and industrial purposes. The uncontrolled dumping of domestic or industrial waste into rivers, streams, or natural sources of fresh water has led to widespread water pollution. So this has led to a decrease in the availability of fresh water resources and increased water stresses. So there are some, already many speakers say the rules, there are n numbers of rules, application in water resource management and development. In very beginning, we can say assessment of water resources. First, we have to assess, we know where it is, how much. Then for development, we require how to utilize it, how to develop it for better utilization. Then another important aspect of water resources is water resource management. And then that's the heaviest management is the flood management. Very unmanaged result of water resource is the flood. So flood management is the heaviest process of management. Already many people had put their interest or emphasized that how important it is, and they have shown the processes involved for flood disaster management. Yeah. So you have heard about, you know many of the satellite data available for different purposes of water resource management and development. The latest satellite images available in India are EOS-04 and ResourceSat. EOS satellites for natural resource management. Some of these satellites like ResourceSat-2A and EOS-04. ResourceSat-2A is an optical remote sensing satellite launched on December 7, 2006. This sensor includes LIS-3, LIS-4 AOUs. These three sensors, both look similar, but they are different by resolution. So we have to see, and a expert should decide which sensor should be used for what purpose. Resolution is different, means the map can be generated out of the satellite will be different and can be used for different scale projects or analysis of analysis for different scale. So I'll talk something on water resource assessment using satellite data. In India, satellite images have been used effectively for mapping and monitoring of water bodies. Space Application Center Ahmedabad has been preparing water body maps at 1:50,000 scale using list 3 data. But after that, using list 4 data, ISRO only used to prepare the same land use land cover map at 1:10,000 scale. And the 50,000 scale prepared by list 3 data is repeated at 5 years interval of time. That data can be utilized for monitoring of the water bodies. Whether the water body is depleting or increasing due to different reasons. Then estimation of water budget is a very crucial in water resources. Different components of the water budgets like precipitation, evapotranspiration, soil moisture storage, and surface runoff are being computed using satellite data with the help of geographic information GIS tools. It means the inputs required for these purposes, we need number of inputs, which finally gives a budget, different component of the water budget, like evapotranspiration, there are sensors. For infiltration, there are also sensors, or you can calculate also, because infiltration is a function of soil. But in GIS environment, the soil map can be incorporated to other parameters like rainfall and all. What is the infiltration rate? Then runoff, you know, it's a function of land use, slope, then the soil type. So these all we can generate using space technology. And you should understand, if you are working for a microwater cell level, then your scale preparation of input data like land use, slope, and rainfall intensity, rainfall measurements should be accordingly. Suppose when you are going for microwater cell treatment plan or microwater cell development, actually you should not use a soil map of 1:50,000. And ISRO is preparing a land use map of 1:50,000, but it should not download and use it for microwater cell development. It will mislead. So that is matter. Now there are so many open source, and there are so many because nowadays nothing is concentrated. It is flashed everywhere. If you Google it, many information comes, but people has to be understand properly, and even the authorities to understand whom to be engaged for what sort of work. Otherwise, it may mislead. Here, one thing is estimation of water budget I mentioned. Then groundwater prospect mapping. Previously, it is already told that how space technology being used for groundwater prospect mapping. It was already told, but ISRO has prepared groundwater prospect map for entire country, but step-wise, first step and second phase already done. But I am not sure whether Mizoram is included in the second phase. It is not. If it is not included, it will come in the third phase. But here, space technology is well included for this purpose, and it is helping that for the planners where to dig, at least for groundwater. Here, actually, we include the groundwater board level data also to prepare the prospect map. So I mentioned as a water budget here. So different components are there. The precipitation. this main rainfall. So for estimation of rainfall also, for getting the rainfall also space technology used. Or space technology, satellite data are there to get us different interval rainfall data, forecast data also there, measured data also there, and then geospatial technology also can be used to prepare a rainfall map in GIS environment using the point data, because we have so many gauge stations, but that is not a spatial data, geospatially. So previous speaker, he told how we can make a spatial map using different extrapolation processes, and we can get a map for GIS domain. But we have to understand there are also so many methods to extrapolate data. So system will give if you put the data, but result will be different. So that need to be checked properly and do that thing. So these different components, the soil storage value, soil moisture storage value, that's MODIS data is giving that thing also. Then, but we can calculate also using the physical parameters like soil parameters, rainfall duration, etc. You can calculate it also, because satellite data is sometimes it is inferring, or it may be sometimes not so very correct. But if spatial cases, you can estimate it, you can calculate it. So finally, for getting surface runoff, mostly we are using CN curve method, where the CN curve is a curve. This is a rainfall runoff relations. It is a function of soil again and land use also. It generates a curve, set of curve, different rainfall intensity. Based on different rainfall intensity, what will be the runoff for depending on the soil type and land use type. For the purpose of the water resource development, NESEC is doing a lot of work. One is that suitable site for construction of check dams. So by now we understood check dams are how important for mostly for terrain like hilly terrains, Mizoram and northeastern mostly except Assam. Check dams is to resist the flow velocity. Same time it protect the siltation in the downstream area. So using GIS environment and space technology input like DEM, digital elevation model, and land use pattern, then drainage pattern, which is also coming out of a digital elevation model. So we can find out suitable locations where you can construct a check dams. For that purpose, users many times ask us, okay, this is the check dam location, how much it will inundate? So using similar DEM value, DEM data, we can find the extent of inundation. If suppose your check dam is 2 meters of height, and what is the, for maximum extreme condition, what will be the inundation area? And another very important work we conducted for water resource development is that is assessment and monitoring of common area. That is, what is this? Actually, Central Water Commission is funding to the State Department for construction of, for development of irrigation common area. But the process is a very prolonged and it is a very fund-consuming method. So CWC wants to apply space technology, whether it is progress or not. So it's a very well use of remote sensing in the field of water resource development, along with ground truth, definitely. So actually AIBP is Accelerated Irrigation Benefit Program. It's a construction of canals, some infrastructure like siphon, whatever required in a command system. Bridge also requires something, culvert, siphon, all those are required. Now we use, here it is clear, this is a Cartosat data, 5 meter resolution. So we use this thing. We got the proposal from the State Department for a certain common area. They used to give us the map, proposed scheme of the common area, main canals, distributory, sub-distributory, where should be the siphon and all. If it is required, point information is given to us. Then we use satellite data to know whether the canals are made or not. This is some example in Assam. See, this is a canal. This is very much clear here. Another canal, it is very much clear. It is visible from the satellite data. But here if you see, the canal is not there. It means no common area developed beyond this point. So based on the length remain unconnected to the previous canal, means previous main canal, that proportionately the common area may be said the common area is not developed. So that's why proportionally seeing the length not prepared, not completed, proportional to the total length, and the area also we deducted proportionately, and then we say the percent of progress of the work. Another important work we done is assessment and monitoring of common area. Okay, this is simple actually, but it is a very good application of remote sensing. Suppose this common area is developed. Common area sometimes they say, suppose actual physical area is 100, sometimes the department says 200 potential, whether potential is used or not. They said the common area will be used for double cropping. But most of the northeastern region, rainy season paddy crops, it grows in the rainy season. So for that irrigation rarely required. But mostly required irrigation is in winter. But then we say, a satellite image very nicely provide whether a crop is grown or not. Already you must be knowing when a crop is grown, the image shows red, first color combination shows a red signature. So, and we very clearly know the common area. The agricultural land is identification of agricultural land using a satellite data of post resolution also, it is very easy stuff. So since we know the agricultural fields, common areas, so we can just subset the areas and set it with a multi-temporal satellite data, basically Rabi season. Because Rabi season only demanded the water supply. Irrigation requirement is more in case of Northeast. So if the crop is not grown there, so we say the potential is not double of the actual geographical area. That way we can say the utilization of the common area. Another important work we did, okay, I'll show you next slide. That is part of that estimation of submergence and the capacity of reservoirs. Anyway, I told about the submergence of the reservoir. Similar way actually, we try to get develop the curves like depth area curve, almost area depth curve of a reservoir. Because you know the depth of the reservoir changes time to time. So the area of the inundation area we can get from a satellite image. But same time, in as far as hydroelectric power, I'm talking about a hydroelectric power. The authority knows at what extent, what is the depth, day-wise. They know every day, they keep record of that. So we get the depth day-wise, and we get a satellite image, same depth. Then we know area and depth. Once we know the relation depth and area, we can get a depth area curve using temporal set of data. So we get number of data and we can get a curve like this. Water spread area with different depth. Then we can extrapolate it to further, and then finally using this type. The differential calculus, help of differential calculus, we can estimate the reservoir capacity, present reservoir capacity, when it is already executed. Because of siltation, the original capacity does not remain intact. So, but we don't know what is the capacity now. And to understand what is the rate of soil loss also. From the graph, we can get the rate of soil loss, and you can then say how long the reservoir will work for generation of hydropower. If rate of soil loss is very high, so it will not last long. then what they, very objective, I have done 3 exercises like this for Northeast India. Their objective is, since due to siltation the reservoir capacity is depleting day by day, so they will lose power. They want to find out the places where protection for soil loss is required. That is soil loss, again coming soil loss estimation. Then I have done for same all this catchment area, same only, prioritization of micro-rotation based on the soil loss. He already told how we can estimate soil loss using satellite data. For estimation of soil loss, we can use very efficiently space technology. This is soil loss function is soil only, basically soil type, preparation of soil map also we can use remote sensing. Same time land use we can prepare using space technology. Then slope also required. That's very good slope map can be prepared using digital elevation model. Then digital elevation model are product of space technology. Then flood management, actually many people told about the flood management. So what we is direct space technology use, flood hazard generation, near real-time flood mapping, that's there. Actually ISRO is doing for every flood, heavy flood, for Assam basically I am talking because Assam is facing flood more. So, what they do for a certain, during this flood season, when the heavy spell of rain is there, they prepare flood map using SAR data, not typical optical data because there is a certain drawbacks. They use SAR data, different type of SAR data. Yeah? SAR data are there and they have different resolution anywhere. Some accuracy we are losing, we are compromising some accuracy, but still we are mapping what is the extent of flood. So they are preparing at least 5-6 times a year. Then we know that we have set of flood map for a certain area. Based on that, repeativity of the flood, so flood hazard generation has been prepared by NRC. So that is very purely space applications. Another very important work I have done recently, I was the principal investigator to. That is what I have written here. Flood water data. So we are hearing very critical topic is flood water data, river linking. It is similar to river linking. There are so many issues for river linking. There are debates, but but it's slightly away from the typical river linking. This is actually a basic concept is from our Home Minister only, Honorable Home Minister, Present Home Minister. He asked NSA to do something in this direction. It's for Assam basically. He said Assam is the main issue is the flood. So, but Assam having lot of wetlands. Why you cannot store the excess water into the wetland? That is his concept. Then after that this is our role, how to address the situation. But one thing, as I mentioned previously, we have a map of series of map of water bodies. If you study those, you will find a lot of water bodies are diminishing, depleting. Many of them are not there, and cross or water bodies. They are not there. While flood-like situation, these wetlands behave like a sink. It reduces the flood peak, it delays the flood. If two floods come very continuously, since it delays, so it may increase the gap and it reduces the peak. So the flood situation issues may be reduced. Then we thought, okay, why we cannot think for rejuvenation of such depleting wetlands in Assam, present in Assam, that too near to flood causing rivers. Then we took GIS and try to find out some depleting wetlands and which are slightly larger in size, at least 10 hectares we consider, just roughly. Then we propose to dig it and then join it from the nearest from a certain nearest point, so the excess water from the river can be filled here and the downstream side may be relieved from flood. And then we find the gradient also, try to get the gradient also, how it is, how the channel gradient will be. So these are some excavation will be required, but this they follow this path, the gradient is mostly natural. So that way we find did the work. Apart from this, we know this wetland is really not very sufficient to accommodate the flood. Then we thought, why we cannot store the source of flood coming? What is the source of flood? It's a runoff only, no? Basically, for this river, the catchment area only provide the flood. Most of the rivers are not groundwater feeding, mostly majority surface water. So why we cannot store surface water? Coming to the river very, very fast, we reduce. And the mechanism developed by us is it will increase the losses and reduce the surface area. Those are catchment treatment plan as already shown. Check them also we decided. We have selected for Mizoram also. Number of suitable site for construction of check dams, which will stop the siltation, as he mentioned nicely. So it will stop the siltation, so it will rejuvenate the wetland also same time. And once you vegetative measure, if you design for some go for vegetative measure for wastelands which are already deforested. Then why anyway IWP is doing like that only, increasing vegetation cover. So anyway it is doing only, but we have to put more emphasis whether it is done or not, whether if it is doing also it is doing properly or not. So we suggested suitable catchment treatment plan for places where forest is already degraded. Degraded lands we selected, and then we suggest for some measures like different type of measures along with check dams. So already told by previous. Am I over the time? Okay. So here very special one sentence I will tell, that is people are using mostly for flood forecasting rainfall data. But that rainfall data is freely available from different sources. IMD also forecasting rainfall. But special what doing by any set is we are assimilating local climatic data. IMD is using global data, because rainfall is a function of many parameters like wind direction, cloud top temperature, so many, I don't know them, but NSF meteorological thing is assimilating local data, using local stations, and they are forecasting, I believe, a short duration forecast or long duration. Sorry. More than long the forecast is, better the final forecast. So long duration rainfall forecast they are doing and helping to long duration flood forecast also. So this is river training work. Already told, we multi-day satellite data we are using to find the soil riverbank erosion. We found recently, this is very recent for Assam, up to 16 to 2002. This is a very automatic system we have developed using free software. Okay, it is a Google Earth engine. Data flow is very free, and we can get the bank erosion district wise. Entire Assam we did very short duration. Every river, almost every river. So water asset management, anyway people are saying most important work we did is monitoring of IWP water set. IWP is implemented by Rural Development, Ministry of Rural Development since 2009. Now they started monitoring. So space technology is used to monitor whether it is progress right direction or not. This is an example. They are constructing water body like this, previous satellite image, present satellite image. So like that we can check it. Whether check dam is constructed or the farm pole is prepared or not. So soil is anyway also I also speak. So next is thank you, I believe.
Thank you so much, sir, for sharing your contribution to Northeast India and also your vision for Mizoram. May I now invite the next speaker, Dr. Larintara, Department of Physics, Pachhunga University College, Aizawl. Dr. Larintara is an associate professor with 13 years of experience and a PhD in physics and has research interests in general relativity, high energy physics, and RF radiation effects. His publications focus on the effects of mobile tower radiation on human health, examining specific symptoms and power densities. He has presented studies on oscillations, acoustics, RF radiation, and health issues near mobile towers. Case studies. He has also had case studies to explore the health impacts of varying power densities and RF radiation in specific districts. Sir, the stage is yours.
Hello, hello. 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 Oh, thank you. When I saw the titles of the speakers, the other 6 speakers, it came to my mind that if I give a talk on the basic principles of satellite launching and home and transfer orbit, it might be useful. That was what came to my mind first. But later, when I considered the different backgrounds for the audiences, and so I thought, if I give a talk on simple ones, like in terms of layman's terms, which everybody can understand, even management background will be able to understand, I hope. And so I prepared a simple lecture starting from the earlier cosmology, and I will end with, if time permits me, I will end with the possible future of the universe. Here will be the contents. I'm not sure whether I can I can finish or not, but at least I'll try. I'll go fast a little bit here. The early cosmology, I'll start with geocentric model. Geo here, geo means earth in Greek. Geocentric model. In this model, it assumed that the earth is in the center of the sky, around which all the stars, including the sun, are revolving. It was put forwarded by Greek philosophers like Aristotle, Ptolemy, even Plato. And when the church became strongly established, the church took it as a divine in nature. And so anyone who opposed this model, this idea that the earth is at the center of the sky, the church used to punish those persons. And we know this is scientifically incorrect. And so I'll skip to the next one. Heliocentric model. Helios means sun, the sun in Greek. In this model, it is assumed that the sun is at the center of the sky, around which the earth and all the planets are revolving. Long back, Indian mathematician Aryabhata had this kind of idea, but who modernized actually was Copernicus, starting from Copernicus. Copernicus was a Polish priest, During his lifetime, he had so many works regarding heliocentric model, but he dared not to publish because of the church. After 1 year after his death, his friends published his work regarding this heliocentric model. We know this is correct. Even today, we are still following this model that the sun is at the center and the earth, all the planets are revolving around it. And here is one incident that Bruno, one astronomer, who was the strong supporter of this model, he was punished and burnt alive in Rome. And might be he was the first who was sacrificed due to science. Even Galileo was house arrested in his 80s. But Galileo supported this idea till his death, although he was arrested. Now, let us look at solar system. We all know, I assumed, what solar system is. The sun, 8 planets, 5 dwarf planets, comets, asteroids, meteorites, all those revolving around the sun. We called it solar system. They are orbiting the sun in elliptical orbits, which Kepler already predicted. We still remember, maybe, in our class 11 and BSc, we studied Kepler's laws of planetary motions. All the objects in the solar system revolving around the sun are revolving around the galaxy, center of galaxy, that is our Milky Way galaxy. Within 250 years, 250 million years, we revolve once. It is estimated that the age of the solar system is around 4.6 billion years. That means from the beginning, the solar system had already revolved around the center, maybe around 19 or 20 times only. I'll go to the next one. Here is the picture, and let us skip it. We already knew this thing from our middle school. Now, Milky Way galaxy. This is our own galaxy. It is so huge that the diameter is around 100,000 light years. I assumed we all know what light year is, and so I will not explain about light year. It is estimated that there are around 200 to 400 billion stars in our own galaxy. We are fortunate, let me say, we are fortunate that the solar system, is at about 27,000 light years from the center of the galaxy. Here, the right one is our Milky Way galaxy. This is too small, I cannot point it. Here is the center, and about here, the solar system is located in one of the spiral arms. It is a spiral type galaxy. There are some 3 or 4 types, different galaxies, among which one is spiral galaxy. The Milky Way galaxy is one of such spiral galaxies. In the center, there is a big, supermassive black hole with approximately 4.2 million solar masses. It is called Sagittarius A, which was confirmed in 2020 with photographs. I mean photographs from different radio satellites from all over the world. They combined together and they got the photograph of that black hole. It is very active. The center is very active because the nearby stars are being pulled and sucked into to the black hole, the center. And so there are lots of radiations and too active. If we are much nearer to the center than this, then there may be no possibility of life there. And so you should be thankful you are placed about 27,000 light years from the center of the galaxy. It is called, this Milky Way galaxy is called Akash Ganga in Hindu mythology. And in a clear night during winter, it is possible to see something like a white river from north to south. We called in Mizo Classic Kong, but it is very difficult to see from the city. But if you're lucky, it may be possible to see it. That white patch, let me call, that white patch is one of those spiral arms. Here we have some spiral arms. One of the arms where we are located is what we are seeing at the night, which we called Akash Ganga or Milky or Classic Kong. Now I'll show you something else, which you may not believe it, or which you may not expect it. I'll compare different sizes. In this comparison, we see the Earth is the biggest. And so let me call big Earth. So big. Look at the Earth carefully. There, here, around here, we see India here. Around here, we are right now. And so you may say, oh, I'm big. Even in this picture, I can see my location, I can see my country, but you cannot see your house, your position, yourself. You cannot see there. But at least we can identify or we can guess here where Aizawl is there or where Mizoram is there. We can guess it from there, at least. Now, what about this? We saw in the former slide that the Earth was so big, but here, the Earth, we can see it here. Jupiter is about 11 times bigger than the Earth in diameter. And so, do you still think we are big? I'm not sure. And then what about this? We used to think the Earth is a beautiful planet, seeing from the sky. The Earth looks very beautiful. And what about here? The Earth, do you still think it is beauty there? It is a small black dot only. Personally, I don't find any beauty there. Thinking about from the scale of the Earth, the scale of the sun. From the scale of the sun, referring the size of the sun, I don't find any beauty of the Earth there. I don't see India. I don't see Mizoram. I don't see anything. I just see a simple black dot there. And so, in fact, according to this picture, in my personal opinion, I find Dr. Frieta is much more beautiful than the Earth. I'll go to the next one. Here is another big star, Arcturus. This is a big star, around 25 to 30 times bigger than the Earth. In this scale, see, we can see the sun there. This yellow one, the smallest yellow, this one is the sun. Yeah, here is the Jupiter. You may not be able to see it from there. Jupiter was so big there. Then can you guess the missing word there? Here? Yeah, invisible art. The invisible art. In this scale, Arcturus with Arcturus size, the art cannot be seen. And so, with this scale, we cannot say any beauty about the art. The art looks like it is not there at all. Do you still think you are big? You are the giant? What about here? Another bigger stars, Betelgeuse and Antares. Betelgeuse may be one of the most famous stars in the sky. It is there in the Orion's constellation. It is a super red giant star, about 600 bigger than the sun. In this scale, here the sun is about the size of 1 pixel. From there, you will not be able to see the size of the sun. So there is no question about the art. Even the sun, practically we cannot see right now. Then what comes to your mind? We human beings have the tendency to think ourselves big. I'm the giant. I'm the mighty one. I'm the one who can do everything. That is the way we think. But looking at the vastness of the sky, the cosmos, then we can only see we are not that big. Looking at your faces, I feel as if you are thinking that, oh, you are trying to make us think ourselves tiny, small. Ha, here. I'm not joking, really. What I'm trying to tell you is that you, including me, all of us are actually tiny, small. The tiny creatures living in this small blue dot, this small earth, this small rock, hanging in the sky by the unseeable force called gravitation. We are such a small, let me say, tiny creatures living in a small rock in the sky, but thinking we can do everything. Here, I think it is time to bring you to Valentine's Day. It was February 14th, 1990. You may think that, oh, you're talking about Valentine's Day, but you saw this picture. What is the relation between Valentine's Day and this picture? The picture may not be clear from there. This is the picture for trajectory of Voyager 1. In 1977, NASA launched Voyager 1 to study outer planets, starting from Jupiter onwards. On this day, February 14th, 1990, it already crossed the orbit of Neptune, and it was about 6 billion kilometers from the Earth, from the command center, Houston. They called up Voyager 1. Hey, Voyager 1, are you still there? If possible, please turn your camera towards the Earth. That means please reverse your camera towards Earth and then take some pictures. Then Voyager 1, fortunately, turned the camera. Actually, the camera for Voyager was designed such that it could not reverse. But somehow, luckily, by chance, they could reverse it. Then the camera was facing towards the Earth, and it took a very famous picture. Can we guess the name of that picture? Anyone from there? Who? Who said the pale blue dot? Oh, good, good. Great, maybe. Here is the picture. From there, you will not be able to see the Earth here. Here is this small pale blue dot is there, here. Those different stripes, here, some green, brown maybe, these different stripes we see here are the scattered light from the outer wall of the Voyager 1. So, even for me, I find to identify the Earth very difficult from here. There is the same photo. Here is the comment by astronomer Carl Sagan. I really like this comment from Carl Sagan. Here, I put it here. Let me read it out. When he saw that pale blue dot, that photograph of the Earth, he called the pale blue dot. Then he commented like this: look again at that dot. That is here, that is home. That is us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every father and mother, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. This was the comment by Carl Sagan. You can add many other things if you like it. Everything you ever know is there on that small pale blue dot. And so the Earth itself is not that big, not a giant. We are also not a giant. So we used to think we are the giant, but actually when we know the vastness of the sky, we may discover ourselves, we may recognize that we are not that big. Actually, we are the tiny one. I'll skip so many things. I'll go to the expanding universe. We know how big is the universe now. It is too big, unimaginably big. But still, it is expanding. From the early cosmologists to Isaac Newton, even Einstein, they thought the universe was static. That means the size is not increasing, not decreasing. The size of the universe is same all the time. But in 1929, American astronomer, through his observations from telescope, discovered that the universe is expanding. The universe is getting bigger and bigger every time. In his general relativity theory, Einstein, since he thought the universe was static, he added one famous term called the cosmological constant term. It was written in Greek letter lambda. Sometimes they called lambda parameter. That was the cosmological constant term. And he added that term to show that the universe is static, since according to Newton's laws, all the matters in the universe will attract each other and the universe will become smaller and smaller. But since he thought the universe was static, to compensate for that decrease in size of the universe, he added that cosmological constant term, which is having opposite effect to the gravity. And so the universe can be static. He thought that way. But since they discovered that the universe was expanding, he called that cosmological constantum was his biggest blunder. So we now know the universe is expanding. It is already so big, but still expanding. We cannot imagine how big it is. Right now, the best estimate, the most common, let me say, the most common estimate shows that the diameter of the universe is roughly 93 billion light years. But still it is expanding. In that big, so vast space, we are living in a small rock, moving around the sun, thinking ourselves big. That is my message. Let me go to the last one, future of the universe. When they solve the expansion equation for the universe, it contained three solutions. One solution is called open universe solution. That means the universe is expanding with accelerated rate. That means the expansion is getting faster and faster, and so it will expand forever. That solution is called open universe. And another one is called flat universe. Here also the universe will expand forever, but at slower rate. Another one is called flat closed universe. The universe expansion will stop in some distant future because of gravity. And then all the matters will attract each other, then finally they will come through a single point. So they will form another cosmic egg, which will somehow explode again, creating another universe. And so the universe will be born again. Such another Big Bang is called Big Crunch. It is favored by Roger Penrose of Oxford University. I think it was 2 or 3 years before. He was awarded Nobel Prize for this kind of model, Roger Penrose. And so we know the universe will have such a kind of ending. From any three of the possibilities, the universe will follow one possibility. Right now, all the observations show that the universe expansion is faster and faster. That means the first one, open universe. If it is really so, the universe will expand forever with faster rate, then all the stars will die out. The universe will be completely dark. It will consist only of darkness. That is called cold end. We don't know if it will really happen, but right now, the observation shows that the universe is open. I end with this quote. I'll not say what it is, but some of you may know whose word is this. And so, I'll end my talk. Thank you for your patience. Thank you.
Thank you very much, sir. A simple yet philosophical presentation that we just listened to. Very interesting presentation. Thank you very much, sir. We will now have a short tea break of 15 minutes. And I request the ushers to guide us to our rest areas again. And our session will continue, will resume at 3:35. 15-minute short break. Government of Mizoram. He is also an alumni member of the Indian Institute of Technology, Roorkee, in the Department of Water Resources, Development and Management. And the title of his presentation is RTDAS, Real-Time Data Acquisition System. Sir, the stage is yours.
Good afternoon to you all again. There is one advantage of giving a presentation at the later stage, because even if you make a mistake, hardly anybody notices. And I feel lucky I don't have to talk about the big cosmos and all. I have to talk about small things. So even if I make a mistake, it will be a tiny mistake. As introduced, I'm to talk about real-time data acquisition system, RTDAS for short, in Mizoram. This RTDAS is established in Mizoram under NHP mainly, and we have additional 2 AWS from Brahmaputra Board project. And we have set up RTDAS from NHP at a cost of 869.31 lakh. NHP is a central sector scheme, means the government of Mizoram doesn't have to input any fund in it. It is 10% grant, and the objective is to improve the extent, quality, and accessibility of water resources information, and to strengthen the capacity of targeted water resources management institutions in India. Targeted means the implementing agencies, in which irrigation and water resources is one of them. So what is RTDAS actually? It is the process of obtaining hydrometeorological data from a remote station which you may not access otherwise, and transmit the data to a receiving station somewhere else on real-time basis. That is the definition of RTDAS. And it usually have sensors, data collection platform, telemetry modem, something to do with transmission, and power supply system, and state data center or earth receiving station, or both. Why it is necessary? You can have a data collection center without real-time basis, but it has a different use. When it is coupled with real-time, then it can be used for objective analysis of water resources. And up-to-date knowledge of water resources helps policymakers or scientists or whoever uses the data for flood forecasting or flood warning, as Dr. Arnab has shown, reservoir operation, water supply management or sector allocation, irrigation planning. I am not going to in detail about these points. Hydroelectricity generation, environmental monitoring and planning, because they know the condition of water at the present time. So let's see, what do we have in Mizoram? Sensors. I'll show the picture of sensors. It senses rainfall, temperature, relative humidity, wind, radiation, evaporation, and other sensors like water level sensor, due to which we can know the discharge of that particular river, and groundwater level also. Let's see how they look like. Just for a brief. These are the pictures of those sensors I'm talking about. And data collection platform, it consists of the mounting, the power supply system, and data logger. So let's see how it looks like. So this is the DCP. Can you see the arrow moving? Yeah, this is the DCP. Here is the data logger. This is the data logger. So that is the DCP. Sorry. And power supply system. Here in Mizoram, we use solar panel and a battery to back up that solar panel. The battery can back up data transmission, uninterrupted data transmission for a continuous 15 days without recharge. Even if there's no solar radiation for 15 days, it will still it will still transmit the data. And the data management system is installed in the data center. It receives the data from the remote sensors, and the practice here in the state, I mean under NHP, is that all the data gets transmitted to National Water Informatics Center through WIMS, we call it Water Information Management System. So that is how it goes. Here it looks very beautiful, not like Satan and all, but still looks beautiful. So this is the setup. This is the automatic rain gauge. This is what we have installed at Buchangpai. So here you see, this is the actual collection platform, the rain gauge, here shown clearly. This is the data logger, this is the battery. So how it works? See, when rain falls, there's a tipping bucket. The number of tips is recorded. It is translated into the amount of water that is fallen on that particular place. That is how it works. So we have established ARG at 27 places across Mizoram. We were discussing about the location of rain gauges. So anyway, this is where they are. And automatic weather station. Automatic weather station also consists of ARG, but not only ARG, it has other many sensors. Like here, these are the AWS sensors, like atmospheric temperature, relative humidity, solar radiation, pressure, wind, velocity and direction. AWLR is automatic water level recorder. That is how high that particular water flows in a river. And at some places we have installed pen evaporimeter. These are the places where we have installed AWS. If you see serial number 1, number 6, and number 10, it has additional soil moisture sensor, apart from number 5 and number 6. Number 5 and number 6, not only does it have soil moisture sensor, it also have evaporimeter. So actually, according to, I am the director here, he would know very well, that Mizoram, only one pen evaporimeter is enough, according to the size. But the thing is, our terrain is hilly, and some are very low, some are very high. So we thought it's better to install at 2 places. One at the middle of Mizoram, and the other to capture the scenario of higher altitude at Champai. And Champai is called rice bowl of Mizoram, so it's very important whether there is evaporation, how much evaporation takes place there. GD station is very interesting. See, here, before also I have shown the non-contacting radar. This is radar sensor. It emits electromagnetic waves and calculates how much it takes to touch the level of water and bounce back. So according to the time it takes, they know how deep is the water, because we have already input the zero gauge. So minus zero gauge and the water level, the depth of water is calculated by itself, but it doesn't show the discharge. That is another big problem. To know the discharge, we have to have rating curve. First, cross-section. Cross-section, we take cross-section usually using 3 instruments. One is DGPS, that is for the exact location, sensitive to millimeters. And the other one is total station, to know the profile. And sometimes we use ADCP because when the river is deep, it's very difficult to use total station. So after knowing all those things and calculating the discharge for a particular height of water, rating curve is made. Once a rating curve is made, only by knowing the level of water, you know how much water is discharged. So that's the working principle of our radar. So we have 22 places we have installed AWLR on 17 rivers. On Klong River, we have extra 5, apart from the original one. Total 6 we have on Klong River because we want to have earlier flood warning system. Professor Arnab has already talked about this particular subject, so I will not go into detail. So, from 17 rivers, the data comes every hour to our data center, telemetrically. I'll show how it comes later. Piezometer. Piezometer is an instrument used for measuring the depth of groundwater. So it can be many types. What we're using is DWLR, Digital Water Level Recorder. It records how high is the water below the ground surface. It gives the data once every 6 hours because groundwater is not supposed to vary within a short period, so once in every 6 hours is more than enough. We have installed 20 piezometers, DWLR, and if possible, we are trying to install another 80 if NHP Advance comes. We proposed another 80. So this is the stations. These are the stations we have under RTDAS. Altogether, we have 21 stations. All 81 stations are transmitting data, most of them every hour, piezometer every 6 hours. It comes to our data center at the basement one of this building. So this is how space technology is utilized. Here we have sensor. Sensor, inside there's a data logger. It stores all the data, but it has to transmit. There we use GPRS or GSM technology, which uses satellite. And it comes to state data center, then from state data center to wherever it has to go, it goes. But GSM or GPRS alone is not dependable sometimes, especially during storms, lightnings. The tower sometimes gets shut. That's why we need satellite. So satellite INSAT is used by this particular RTDAS, and we cannot directly get the data from INSAT. It has to go through ERS, Earth Receiving Station. So we are using one Earth Receiving Station owned by CWC. CWC people are also here. So all the NHP implementing agencies are using ERS owned by CWC. So there are two ways. One is through INSAT, one is through the GPRS. So we hope to have continuous data. But unfortunately, practically speaking, it's very difficult. For example, there was a problem with INSAT for about more than 2 months. And recently it has started working again. But that also, some parts are not working, some stations are not giving proper data, proper transmission, so as to say. Especially our GD station, those are located along the rivers. And rivers, as you know, are within Mizoram, within very deep gorges. So some places we do not get mobile signal, GSM signal. So that's a big problem. So we have to rely on INSAT at many places. So here all the data comes to our data center. This is a picture of our data center at this building only. So this is the hydrological information we have now. The sensor comes to data logger, data collection platform, then gets transmitted either through satellite or GSM to our data center. Then it goes to NWIC or any other places. This is what is called hydrological information system. Now Mizoram is planning to have State Water Informatics Center, as our Honorable Minister has said this morning. It is under proposal. Let's hope it comes very soon. And for State Water Informatics Center, the department is preparing itself. Now we have made this website. It's not fully functional as yet, but it's in the process. Does it have internet connection, this particular laptop? Is that, okay. Let me try. Just to show a few places, This is our website. Under here, we call it MZWARIS, stands for Mizoram Water Resources Information System. If you click that one, it will take you to the website we are working on. It is not yet fully functioned. And since last night there was a problem with NWIC, I don't know whether it has rectified or not. So here all the stations are shown: ARG 27, AWS 12, AWLR 22, DWR 20, water quality. Water quality also we started taking from some stations, because PH is taking water quality, but only from the point of domestic use. And Pollution Control Board, SPCB. Am I correct? SPCB, State Pollution, SPCB. They are collecting from many places, but they cannot collect from each and every corner. So we are helping each other. We are collecting from such places where either PHE nor SPAB, SPCB are not collecting any data. So it will be complementary. And another thing is, nobody is making any examination whether the water is suitable for agriculture or not. That is our specialty, so we are determining that. So if you click this one, it will give you telemetry as well as non-telemetry. Now we are talking about RTDA, so it's telemetry only. We have ARG, AWLR, AWS, DWLR, all these stations. Let's say I click this one, ARG. So it's not moving. Let's see. Oh, it's moving. And the speed is not my fault. ICT people are here, I think. It's their fault. NIC. See, this is groundwater. It will give you many informations, like the temperature of that particular place. Here, suppose Champai, it will give you the temperature, it will give you what else? The level and the location and how high that particular piezometer is from the mean sea level. It will give you all those things. And we have decoded this DWLR successfully so that we can give to anyone. But I don't know, for some reason, it's not live, I think. It's supposed to come live. This is which day? David, which day is this one? Huh? 14th. So sometimes it doesn't give signal. I mean, that particular station may not have signal for some time, so this is the latest one we have. And this is the graphical presentation of the particular piezometer from January, I think, January till August. So the bigger the black portion is, the higher the level of water. That means the nearer it is from the ground level. So like that, it will give you information. And suppose we go to other places, like water resources, rivers. Here we are building a network of rivers under GIS platform. So list of rivers, suppose you click any one, it will show you where it is and how long that particular river is. So we are working on this. It's not yet very rich, but it will give you some information. And like if you go to the basin, Mizoram is divided into 3. So these are the, suppose I go for Klong. It shows the total catchment area of Klong, and it will show you the area, and you can go in detail. Can we? Suppose I go to Salalui. Salalui is in the southern tip of Mizoram. See, this is the Sala area. It will give you the, why it's giving? Yeah, it shows. So like that, we are building this website. Later, we hope it will be very useful for other departments as well as research scholars and those who want to use this information. Here, flood warning system will be displayed once it is ready. The condition of Klong, whether there is warning or not, where the likely inundation area would be, here it will be shown. But as of now, it's nil. Here, GIS platform, we are planning to do so many things. Like, for example, LULC. If you click anywhere, we want to show the LULC of that particular place. But we are yet to develop this one. And peak discharge also. Suppose you want to make a check dam. You select the location. You just click that particular point. We are planning to show how much is the catchment area, and we are planning to show the peak discharge of that particular point so that you will be able to design your check dam. So, gallery, I don't know what are there. Let me just click what are there. Okay. These are some pictures. We are planning to use Google Earth Engine platform and integrate into this MZ Worries for anybody who is interested in GEE. So that is what we are planning to do in the future. Some are working now, some are yet to work, some are under development. And once our SWC is officially passed by Mizoram government, we can go into full swing. So RT the expected benefits for Mizoram is, we hope we will get a reliable hydromet data for different departments. It's not only for irrigation department, it's for all those who want to use. It may be institutions, it may be individuals, it may be research scholars. And once you have the data, the information, and you pass that information to policymaker, they will be able to make a very well-informed decision making. For example, Mizoram is yet to have sectoral allocation of water. Suppose there is acute shortage of water along this Klong River. So policymaker will be able to allocate that much water should be for domestic, this much for irrigation, this much for industry or something like that. So they can make a well-informed decision based on this data. And environmental flow is becoming very important, and Mizoram is yet to have any fixation of e-flow for all the rivers. So based on the data, we will be able to fix e-flow, so that even if somebody wants to build a dam, they have to release the e-flow. And flood warning system, we are working on it with NERIST. And weather forecast also based on all those AWS. And crop water requirement, irrigation scheduling, I'll not go into detail. And the public itself will know how much water we have and how much we are like to have in the future also. And especially for research scholars and modelers, this will be very, very helpful. And that's all for me. Thank you all.
Thank you very much, sir. The presentation that he had just presented had clearly highlighted the development that the department had made towards the progress of the country and the land. Next, we will call upon the stage Mr. V. Thang Thuam. He is currently a surveyor of the Department of Survey of India. And his field of activity includes GPS leveling course as well as drone. Sir, you may proceed.
First of all, I thanks to the organizer so giving me a time for this presentation. I will, on behalf of Survey of India, today I'm going to present in regarding of course. I think you might have heard course before. Before we have a lunch, I think one of the sir has mentioned regarding with course. In regarding with that one, I'm going to present this what is course and what the use advantage, plus how to access course. So we'll start the presentation. Geospatial data and spatially aware technologies are key for a smart nation. Almost every aspect of a nation has a spatial component. Monitoring and understanding our ever-changing natural and human landscape require continual collection, storage, processing, integration, synthesis, and dissemination of big geodata. National Spatial Reference Frame. Previously, we used to use great trigonometric survey average datum. Then we go to elsewhere NSRF through GCP library. Now we move on to reference, active reference frame through course network. NSRF, National Spatial Reference Frame, was established through a passive network of about 260 well-spread GCP ground control point at a spacing of 250 to 300 kilometers apart across the country during the period from 2006 to 2008. The network was further densified with 2,260 precise ground control points at a spacing of 30 to 40 kilometers apart within the framework of NSRF. The NSRF is only suited for relative positioning, primarily for mapping application. Course-based NSRF. Survey of India has established most of the course in different locations of India. In Mizoram also there is roughly around 12 course station. Course network would be the active ground reference mark. It will ultimately replace the passive ground reference mark, that is GCP library. This will provide real-time positional accuracy of less than 5 centimeters. This will improve the productivity and reliability of surveying and mapping. The course, once established, could be used by any state agency, department, namely Revenue Department, Gram Panchayat, Public Works Department, Rural Development Department, Agriculture, Drainage and Canal, Education, Electricity, Water, Health, etc. for the survey and implementing or using GIS-based application. GNSS. I think everyone has known GNSS because it has been told before, so I'll skip this one. And this is regarding how the position has been or location has been determined. This is some formulas. If anyone wants to study, you can go through it. I will skip this one. There are many error which we face while getting GNSS signal. So this is regarding the one. And this is the error, ranging error, like satellite clocks have plus minus 2 meter orbit error has plus minus 2.5 ionospheric delay plus minus 5 meter, topographical delay plus minus 0.5, receiver noise plus minus 0.3, multipath plus minus 1. Real-time versus post-process. Results are available in the field, so check can be verified immediately. Stacking out is now possible. One course receiver support multiple rover. No post-processing time required in office. All the survey work done using course will be in the common, consistent national reference frame or datum. Further, the service will be integrated with various GIS applications. So what happened in real time? Data is logged simultaneously at course and rover. Base corrections are transmitted by net-trip link to rover. Rover is initialized using data from base. Data is processed inside roving receiver or controller. Survey is conducted with processing within roving receiver, continuing throughout. Results of processing are sent to controller for logging and viewing. Result. View may be either latitude, longitude, or ellipsoidal heights or noting, easting, or elevation. Initialization, determination of integral wavelengths count up to the satellite required at beginning of all real-time survey, required in the middle of survey if continuous track of at least 5 SV in common with the base has been interrupted, loss of log. Advantage of network RTK over single base RTK. This is a comparison between the single and the network RTK. So in single RTK, standard RTK, it has shorter, and our network RTK has a longer perimeter. Advantages of network RTK over single base RTK: increase operational range, improve positional accuracy at distance, increase initialization speed at distance, the accuracy of the computed rover positions are more homogeneous, higher reliability and availability of RTK correction, support multiple rovers, users and application, no need to pause, process and adjust data to NSRF. How this picture depicts us how the course network is working. And course, real-time positional service. Continuously operating reference station, GNS network is used for providing fit-for-purpose positioning. Corrections are instantly sent to the rover receiver from control center, which help to find very accurate positioning of rover in real time. Course network has integrated national setup. Network-based real-time kinematic positioning is considered to be a superior compared to real-time kinematic, which is highly effective by the distance-dependent error such as satellite orbitals and atmospheric bases. Continuous operating reference station course network envisages is one such model that currently model the distance-dependent error. The GNSS course network infrastructure could be used as a platform for real-time centimeter level accuracy service. This is the course station which we have installed in a different part of India, and there is a side elevation view and front southern view. Following services are being provided by Survey of India using the course network. Real-time positioning service, network RTK services for 3 to 4 centimeter real-time positioning, differential GNSS service for 30 to 40 centimeter accuracy, real-time positioning, reference data services, online data processing of static observation with respect of course, downloading of raw data of course station for processing in user software. User can access the NRTK positioning service from the course portal. Requirement for accessing real-time positioning service, RTK or DZNSS enables GNSS instrument compliance with RTCM and NTRIP protocol. Controller, tablet, maybe mobile, maybe laptop, which work with Windows, iOS or Android. RTK field software that will be Trimble Access, Leica, Xenon, Connect, etc. with requisite DNSS RTK license. Real-time positioning service, accurate coordinate to user in real-time even with the non-geonetic GNSS equipment. User can get the correct feeding from the network processing center, course control center in real time via Ethernet, which is used in the accurate positioning. This is a causes service offer, the plan, the charges, and the remarks. This for DZNSS, where you can get the services, plan, the charge for public, charge for private, and remark. Even very basic GNSS devices which uses only code solutions can also achieving accuracy of 30 to 40 centimeter. User can choose Out of above two services, he can either process its GNSS data with reference to course network online on above said website, or download Rhinex data of nearby course station and use them as master station. Process his static observation data in his own GNSS processing software. Reference data services, online data processing. Survey of India do provide an online facility for processing the user GNSS data. Just upload your GNSS observation file and you will receive the process coordinate. Means we need not to go to the office and do processing. We can do at the field itself after completing the observation. In this regard, there are different services provided by Survey of India, and the plan charges of for public, charges for private, and the remarks. Reference data services, course, VRS, data download. User can download data of any course station. He may use it for processing its own observation in his own processing software. Here also, service offer is there, like a course VRS data download, the plan, charge for public, charge for private user, and remark. Regarding the pricings of the course service offered by Survey of India, you will get in this website, course.surveyofindia.gov.in, subscription charge.php. Benefit of course network, time and cost saving. Single survey grade GNSS receiver with access to the internet can receive course correction data and compute centimeter level accuracy position. Easy of use, accurate positioning with a course network is also very easy to achieve. Coordinate accuracy and homogeneity. A course GNSS network provides a significant benefit that coordinate accuracy is maintained throughout the network, even over large distance between the reference station and NRTK rover. National Spatial Reference Frame. Course network is essential to provide a framework for a unified geodetic reference network that provides a consistent, homogeneous nation with 3D coordinate system. Traceability of coordinates. Pan-India course network will provide dense and continuous feed of plate tectonic motion, which will be beneficial in retracing lane partial coordinates over large time gap. Use cases of precise positioning services. This is application one where we can use course for getting data. This is the second application through drone navigation. This is application 3 where autonomous vehicle has been used. And application 4, automatic machine, smart machines. Application 5, hazard monitoring. Application 6, precise farming. And to access course, we need to have a registration. The registration will be get from this website, www.course.surveyofindia.gov.in. You can check on this website and click on the register. A registration page will open, and you have to select the region according to your region wise. Give a mobile number, the OTP will be sent through that one, and some of the documents has to be uploaded. This is the course registration form. This has to be filled and upload document, then click on submit. And a registration will be successful. There is a guide and SOP for the above also. There's a video tutorial also where you can check it on how to do registration. And for any inquiry, you can mail to course corsgrb.soi@gov.in. Thank you.
Thank you, sir, for your presentation. We will move on to the panel discussion, and some seat arrangements needs to be done. So may I ask the ushers to delegate where to sit. So for the panelists, we have all the presenters, as well as Professor R.C. Tiwari, Senior Professor, Department of Physics. He is also the former Dean, School of Physical Sciences. He is an avid researcher with more than 50 notable publications with total impact factor of 22.054. He also has several experiences overseas as well. We also have Professor Lersha Zwala, currently the head of Department of Physics, Pachhunga University College. He is an alum of IIT Guwahati. He has published notable articles in highly reputed SCI and Scopus Index journals. And then we have Dr. Lelsang Zela Silo, Assistant Professor, Department of Civil Engineering. He is also an alum of IIT Guwahati, and he was also an Associate Professor of Vellore Institute of Technology till 2015. And for the moderation, for our moderator will be Professor Sumit Sen from the Indian Institute of Technology, Roorkee. Professor Sumit Sen is a professor and head of Department of Hydrology at IIT. He also serves as a joint faculty in the Center for Excellence in Disaster Mitigation and Management. With a bachelor's degree in agricultural engineering, a master's degree from University of Arkansas, and a PhD from Auburn University, Professor Sen's research focuses on water movement in watersheds and runoff generation mechanisms. May I now invite all the panelist members to come to the podium. Yes, I think so. And I will hand over the stage to our respected moderator.
All right. So this time we are going to take some time what we all been hearing for the whole day. So I would like to thank all the panelists to be a part of this discussion. But before we go to the panelists, I would like to open this time for our young generation who has been hearing a lot from the morning, and also the participants from the different line departments who have been here. If there are any few quick questions from your side to talk and to discuss with the panelists and the presenters who have done that. Any quick one or two questions specifically for the presenters? We heard many presentations. Or should I start asking the quiz I was telling the students? Yeah.
Good afternoon. Yes, I'm from Sudan. My name is. Yes. My name is. So I'm from Sudan. Currently, I'm a research scholar in Mizoram University Department of Environmental Science. I'm very thankful to all the presenters. They present very valuable information because we are living in the era of like in a technological era. So we as young generation, we really want to be technologically smart. So my question both related to Dr. Raja and SH9. So Dr. Raja, he covered the various applications of the space technology to environment or to our earth. So my question is, both of you, everyone can answer, but Dr. Nair, he highlighted that how we can assess that soil erosion using space technology, and very good presentation that he used the Russell model for estimation the soil erosion. But my question is, okay, we know that through satellite, we saw that how much the soil by 5 classes. So my question, that is in the soil erosion. If I want to measure how much is sedimentation and where it is, how we can calculate the question? Thank you very much.
Dr. Nayak, just a quick suggestion that if we can have the answers little brief, I think it also, yeah.
Turn off. It's off. Or maybe that should be off.
Yeah. The presentation which we made here is to evaluate the erosion potential. Erosion potential is one thing. Taking that sediment from one location to the nearest river and then ultimately to a basin. Basin in most probably it will be a reservoir, or it can be further down to ultimately to the sea level. That is the ultimate basin. That is a transport mechanism is there. Slightly data and additional analysis is required to find out whether this potentially available sediment is really moving from one location to the nearest stream, and where it is further eroding, where it is reworking, further modeling and further studies are required. Here is an evaluation whether the sediment is detachable or not, whether that potential is there or not. Once we know that the potential is there, then we can start thinking of preventing that sediment to move to the nearest major stream. That is the study, and further modeling and further studies required. Transport model, that is. That we haven't touched on this presentation.
Thank you. Yeah, very briefly. Yeah.
Just I want to add one
Yeah.
sentence. To know that where the sediment will yield and deposit. Actually, there is a method called Morgan and Finley. This method, in this method, the potential is also shown. Then whether the hydraulics is sufficient to carry the silt to be yielded or not. That compare. And to understand what is the silt in a certain point, certain outlet, then we should go for the MMF model, which considered where hydraulic energy is more or potential is more. So whichever less is considered. So that you get a yield using MMF.
Thank you, Dr. Bhatt. Yeah, any other quick caution for any specific presenter? Yeah. You have to turn your pages and see what you have written. All right. So maybe my thoughts for the presenters may help you to think and bring back what we have been hearing. So I have made some few points for the presenters especially, and I will also like the other panelists to maybe pitch in when there is any specific point you want to add. So what we have been hearing is that we are talking about water resource management, and water is not a problem, but it can be a problem when it is too much or too little, right? So now my question or my thought here is, as of right now, the space technology, how much it is accurate, or what is the focus right now? Is it on the too much part or is it on the too little part? Any one of the panelists would like to say anything with your experience? Yeah, Rajaram.
In my point of view, it is towards the too much part. It is not the too little part. As of now, through remote sensing, water, where there is water we can see or we can detect, but where there is no water, there is no way.
Yeah.
So I would believe that it is towards the too much part.
Right. So for the students to think over is, why I'm saying is the too much part is the, when we are talking about too much rainfall happening, because of that the floods are happening, then the landslides are happening. So too much part is more focused, but the too little part is of the order of, like when we are talking about the water scarcity, right? So maybe any other thought, like
Yes, sir. I also feel both are means of the same coin, which which cannot look into which one is higher or lesser. Even though here we receive a lot of rain, we have a lot of landslide, and during dry season, almost all the rivers run dry. You know, like we do not have enough water to pump out to the public for supply.
Right.
So, as Dr. Like Professor Subramaniam has pointed out, there's a lot of landslide, but we need water conservation mechanism also in order to retain the water during this monsoon season. So these two has to look into, you know, like so that we conserve the water as well as we are safe from hazards. You know.
Thank you.
Sir, I would like to agree with him on the too much part, but the too little part is not completely absent. I mean, you are correct in pointing out that the focus is right now on too much.
Too much.
But still we can predict well in advance agricultural droughts, meteorological droughts, or even if you think about transferring those on-site data in real time to our analysts, then they can also see.
We have never seen because of the topography. So the remote sensing pictures, when we analyze properly, so I think that, and that is being done also, but if we focus more on this aspect, I feel that can help us, especially place a state like Mizoram or other hilly areas where there is a lot of forest cover and there may be hidden water bodies that could really we could find out and we could reduce at least the water scarcity problem. Thank you.
Thank you. Yeah. We have it too here.
So for hilly terrain like this type of Mizoram kind of, really you need a better scale work. For that you can go for UAV survey also. Now it is very much coming up. So since it is very important mapping of the water bodies, so you can think of that.
Okay, thank you. So basically what we heard is that as of right now, the space technology, and all of us, we are a part of it. So we are focusing more on the too much part, but yes, there is space technology can be utilized towards too little part also when we have the water scarcity issue, right? And we all faces that. So I'll take up the last part of Das sir, what he said about we can go to a high resolution. So we all know that when we're talking about the space technology or the remote sensing imagery, we are talking about two terms. Normally we say spatial and temporal resolution. My question now here is like, how are we going to deal, or how are we dealing with the uncertainty? See, still the image is being taken from up above, but there are still uncertainties are there. How are we dealing with the uncertainty in the remote sensing or the space product? And is there a way like how to do the validation? Maybe Dr. Sanjay would like to say something? You have applied a lot? Yeah? Or maybe anyone else, like, yeah. Open to. Is my question, yeah? Yes. So for the students, we talk about uncertainty is the error part
in a particular image?
Sir, definitely remote sensing always associated with a certain amount of ground verification. Whatever we are interpreting, suppose I prepared a land use land cover map, I need to verify at least 10% of the area by direct field verification. Another thing is that whatever model we are generating, whether it is erosion model or a flood model or whatever it is, with the observed data we are calibrating and then we are validating it. Then that amount of uncertainty will to a great extent we can reduce. And correct georeferencing and usage. Now the course data is available, and the correct latitude, longitude values we are getting, correct georeferencing is possible. So positional accuracy is to a great extent we are managing nowadays. So uncertainty will be certain percent, 100% we may not be able to remove, but to a great extent it can be reduced. That is what I feel.
Thank you. Anyone?
Yeah, sir, actually, my thinking goes in this direction that it is very important when we are using remote sensing products in our models or whatever we use as an input, and then we are doing something else. So first of all, we need to separate the uncertainty contributed from the remote sensing data, and then when I am using it my model is again putting into some another level of uncertainty.
Right.
So first partitioning is required, then only we will be talking about removing them slowly. Now if you think over last 10 years or so, little bit more, then this accuracy and resolution of remote sensing products have increased like anything. I mean, initially we were happy with say 30 meter by 30 meter pixel. Now we are talking about 0.5 meter, even sub-meter level and even in centimeters. So positional accuracy is increasing. Of course, it depends on the user how much detail they work on their ground registration and all. After that, nowadays we don't really talk about going into field with a DGPS and really verify whether how much accurately I have made my identification. So that is an important part, which of course will be there always. So with that, and when the user is knowledgeable enough, experienced enough to use that with the certain doubt in the mind that we may have uncertainty in this, so probably we are, as far as applicability is concerned, I think it's of a great help when we use remote sensing products. Because if you want to gather the same amount of data by some other means, then it will be lot of efforts and lot of money and lot of other kind of uncertainties. So you have to choose, right?
Right. Very. Yeah.
What I even feel is when we talk about mapping or like trafficking, then the accuracy is good. But when we apply in hydrologic field, then we are relying on lots of empirical formulas which are having a lot of uncertainty. So even though the picture is clear, but validating the results with the physical phenomenon is still a challenge.
Okay.
So there we have to have some kind of forward movement.
Yeah. Rajan?
Yeah. I just want to give two examples on that.
Yeah.
That one. The remote sensing, when you say remote sensing, we start with image processing. Right. So that is the first time that we process an image where we validate the image. That means, suppose if there is a data, it's a cloud cover, then we use the back days data to fill it. Now with the availability of SAR, radar images, cloud covers are gone. Now very simple example that when we use an altimeter, we know that there is a river gauge. That altimeter data we always calibrate, and it is calibrated now. So anywhere we see all the NRC data, they are calibrated. Even the ET flux, they have 19 stations of ET flux. So whatever satellite data from NOAA or wherever they generate, it is always calibrated with the 19 and then it comes to us. So for that reason it takes 3 days delay. 500 meter, 5 kilometer by 5 kilometer, but 3 days delay. It is only because of that processing. So
thank you.
Yeah, one thing I add. Actually, the level of uncertainty depends on the data used, as you understand very clearly. So higher the resolution, lesser the uncertainty. Higher the radiometry, lesser the uncertainty. But when the lesser the uncertainty, the image cover is generally less and it increases the cost. Because if your study area is high, then you have to go for multi-sensor or multi-scene satellite data. So generally high radiometric, high resolution satellite data are of lesser SWOT, means it's cover less area. So to cover a better area, study area, you have to get a number of scene, so it increase the cost. So it's all uncertainty actually depends on the user, definitely, how he is going to use the data.
All right, thank you.
I'll add one more thing.
Okay.
It is for NRSC.
Last one.
Recently, because of the open data policy, almost all satellite data of a given resolution is free of cost.
Yes.
So that we can see. Simply go to the website, and from there, just find out that which images. Like previously, all the list 3, list 4, all are free. Because, like I think sub 5, they are charging, chargeable. Anything above 5 meter resolution, and that is very good enough. Because we started with 23.5 meter resolution. Yes. So now it is almost free.
Thank you. So what we heard is basically, okay, the products are getting, the uncertainty or error is getting lower and lower in terms of space and temporal resolution. The quick question is that, okay, when we have a good products, can maybe one or two people, anyone can give an example of a product which is publicly available? See, everything what we are doing as a science is for the society. What are those products coming out for the public? Be it at an urban level, be it at a farmer scale level. Are they available for the society? Are we at that stage? My question, I think it's clear, right? Yeah.
Where to start with? Like, we start giving examples?
Maybe, yeah, one success story or where the product is there which is readily available for the public.
I'm just like not getting this website name. I'll just maybe.
Yeah, sure.
I also not tell the website exactly, but I can say the example that which is going to up to the farmer level.
Not going to. What is available right now?
Yes, it is available. Means it is reaching. It is reaching farmer. That is soil health card.
Soil health card.
Soil health card. It is prepared under ISRO, but it is not.
At what level? What scale?
It is blaze level. It is paddy field level. It is going it is the highest level of requirement.
Okay.
I am telling.
It is actually farm level.
Yeah, I am telling the farm level. So, but it is not in pan India. It is selected because it's very time consuming for soil scientists. We don't have that much, but it is going on.
Thank you. I think so. Soil health card for the farm level. That is basically might be a product of a space. Technology which is being useful for the society.
Yes, sir, I think I can add one more, which was an example of Assam only, and from your division itself. So, sir, in probably in 2008 or 9, this idea was started by CWC, the then executive engineer of Guwahati office. We had a long discussion, and then it was taken up by NISAC. So, even each and every citizen of the affected place where a flood is going to come or may come is getting individual SMS to their mobile phone. So that you cannot go at a higher resolution than person.
Thank you.
May I?
Yeah, Raj.
CWC had an MOU with Google. So whenever we are in the affected area, that Google map shows that this is a flood affected area. So that is the first one. Second is Bhuban portal. When we go to Bhuban portal, there are ET maps available. They are 3 days old, but these ET maps are available. Because see, that processing time is 3 days. So normally they take 3 days. 500 meter, like 5 kilometer by 5 kilometer grid, ET maps are available. And now we know all weather satellites, they are always, grid data is always free.
Yeah, but sometimes they are not useful or not understandable by the community, right?
The question is all the products are available. We are also using free products from NASA, SRTM and all. But whether we are translating them into useful products for our people, that's the question.
Yeah. Anything more?
So just adding to that, because as our friends already said regarding the satellite data. So in 1991, I was attending the program in training in IMD Pune. in the meteorological department. So that time our accuracy of forecasting was just 60%, which is now manifold, very high, very accurate. And especially if I mention the cyclonic things. So in cyclone, I think our accuracy is around 92% or so, maybe more than that. So this is the product which is really very accurately available. And recently we have seen the cyclone which hit this western side, the Gujarat area, how proper monitoring was done with the use of satellite data, which actually made the losses almost nil. It's wonderful outcome from the space science.
Thank you. Anyone else would like to add something here?
One more example that which reaching to the message SMS reaching to the individual level also, that's thunderstorm warning. Actually, it is NSEC also part of that with IMD only, I believe. So, but warning of thunderstorm is still very critical or infant stage till now. But still, whatever whatever the level of accuracy, it is now via district level disaster management authority, it is reaching to the individual level.
Thunderstorm prediction. Thank you. So we heard that, okay, thunderstorm prediction, the soil health cards for the farm level, also about the floods from the Google. So I think these are the different products, and the SMS for the flooding or the thunderstorms are coming up, right? So I'm again going back to the students and the audience. Did something spark to you to, okay, what you heard and you wanted to ask?
I have a couple of questions from my students. Yeah.
Yeah.
They have conveyed me their questions.
Oh, yeah, that would be great.
If you may, yeah.
Please.
Yeah, this is on.
Yeah, this is on now. Yeah. All right. Say I'm a professor in Pachhunga University College. So my students are here and they have passed on their queries from the discussion and from the presentations. So there are a couple of questions here. The first one I would like to ask, if you permit, Mr. Moderator, to Professor Arnab regarding that flood warning system of Tlong River. So I think the audiences, they were very interested in that topic. And the question is like this. So you have installed some early warning systems at some locations at the upstream rivers and all. But in order to really predict the water level at the lower stream and all, should we also consider debris flow from the tributary rivers? So I think in our case in Mizoram, this is something we really need to consider, not only the main Tlong River, because when it comes to rainy seasons, that contributes a lot to the flooding and the water level raise in the Tlong River. So what do you have a comment on this?
I am very happy whoever has asked this. And you prefer to be anonymous, so you passed on to your professor the question. Anyway, so the thing is that right now whatever we have done, with which we have already achieved an accuracy of 30 centimeter height, is only by modeling the upstream gauge and the downstream gauge. But of course the forecast lead time is about 24 hours. We cannot go more than that. But once these AWLR based modeling is finalized, then we have a plan to incorporate the rain gauges also. Once the rain gauges are taken into account, they will be able to capture the signature from those small streams, because it's not, I mean, monetarily possible to install AWLRs on every small streams that we have. It's not possible. So let us optimize somewhere, like the uncertainty, that we will have the main streams gauged, whereas the contribution from the smaller streams, which of course can contribute to flash floods heavily, so then we will try to capture from the rainfall they are receiving. And these inherent machine learning algorithms, they are capable of doing it. Of course, I personally don't like machine learning, because machine learning is going back into science. Earlier we used to do empirical modeling without going into that physics of it. Input and output, I don't know what is happening inside. But from an application point of view, from saving lives point of view, I think it is helping us, so let's use it.
Thank you.
At the same time, sir, I have one suggestion for you. It's just reminded me that if you are calling your surface radars AWLR and groundwater level radars DWLR, it is very difficult to understand from an user point of view. All are digital, all are automatic. So please name the DWLR piezometer or ground level well or something like that.
Yeah.
How do I know which one I'm clicking, AWLR and DWLR?
We'll move forward because I don't want to also delay Chief Engineer Sir's talk. So maybe quick questions and the panel.
One more quick question. Actually, my area of research is photovoltaic materials, but I have some colleagues in our institution in geology department doing research on groundwater mapping and all. So to Sir Dr. Rajaram Purohit, so is there any way that we can access satellite gravity data for this kind of research at the educational institutional level? So if you can open to a collaborative work, my colleagues at the Department of Geology are very eager to hear that, sir.
Frankly speaking, I am not exactly into that work, but it is available.
It's open. It's open source.
It's open source, so anybody can download and use it. One of our colleague who works in Central Groundwater Board, so I can always refer him.
Yeah.
He is Salendra Dwivedi, so he works. So I think he can help.
Yeah, it's
Grace.
yeah, it's open source data.
All right. So
It's
data
just the
are-
processing will require some hand holding. Yeah. Any other quick questions?
There are a couple of questions, but I think you can continue the
Yeah.
question for now.
Yeah, just to think little ahead of it. So we did talk about the quantity in journal. Anyone from the panelists or maybe also the users in the audience, how are we using the space technology towards quality? Any thoughts? It's water quality. But are we thinking in that direction? Are we moving in that direction?
Yes, there are certain uses of space technology in water quality, directly or indirectly. It may be very preliminary level, but it is there. Thermal band we use, and we can see turbidity level. We can see turbidity level. We can see the temperature, and indirectly we can seeing the color. Suppose a water body color is different, means it means different. So since we can see the color from satellite data, so there are certain links which will provide the quality or status of that portion of the water body.
Right.
Yes, rightly said, because many of the plain areas which are having a lot of wetlands, eutrophication and all is being under a lot of research work. Here in Mizoram, we have a lot of suspended sediment concentration, SSC.
Right.
And the NIR bands and all are very much reflecting that, because we have seen that the reflectance in visible region is very less. So we need a multispectral imaging to do this analysis. But the width of the river, as it is quite narrow,
Right.
so there is a chance of missing out the pixel. So that is the problem which we face. But if we get a better resolution, we will be in that process of doing the quality map.
Thank you.
Sir, in the state of Haryana, which is a water scarce area, and pond water is used for the drinking and other purposes.
Right.
So they measure water quality based on the turbidity, and they forecast it through their website, and people are using that. So water quality is there. And in National Hydrology Project also, some of the automatic water quality parameters measurement is there. It will be transmitted, and the way water level and other things are working out, but parameters are very less.
Right.
We cannot, because the inherent quality only through chemical analysis it will be come out, but some of the parameters monitoring and transmitting it.
Okay. So I'll just add to that also, like, see, remote sensing or the space products can be used, as Mr. Nayak also mentioned, Das, that we can develop the water quality indexes also based on the space product. Yes, the space resolution is important, spatial resolution is important. for the water bodies, we are talking about water bodies mapping from the space product, but also the quality component in terms of chlorophyll indexes, we can develop those. And space products are very much useful in that part. Going to my last...
Sir, sorry.
Yeah, maybe...
That's very important point.
Right.
I believe everybody will laugh because students are asking that question regarding the flood. Just I wanted to add one thing. What NISEC is doing, since I showed there also, NISEC, as I mentioned, they are using first rainfall forecast. Rainfall also forecast has a different time, 24 hours or more also sometime. Yeah. So based on that, actually for surface runoff, because every flood is has a good contribution of surface runoff. Surface runoff depends on the rainfall. So rainfall, actually we are using forecasted rainfall for calculate the runoff. Then we go for this hydraulic model to get it. So that way we can increase the forecast period.
Okay, thank you, thank you. So I think we are at 5 o'clock. So maybe another 5 minutes. Can I take 5 minutes more? So maybe just a quick last thought from all the, normally I end the panel discussion this way. So I would like to ask so that all the panelists who have not talked or spoken, can you just name, and I need only one or two words there. What product you rely the most as a space product? 1 or 2 words, that's it. Which product, space product? Maybe starting from that corner. Yeah, sir. कौन सा space product है जो like we use it the max, which you think this is best one?
Imagery is only we are using for mapping.
Right. Okay. Thank you. Yeah.
DM.
DM. Yeah. No, which DM? I think
topography, SRTM,
SRTM is good.
Yeah.
Better than Aster?
Comparison has been done.
What about ALOS Pulsar then?
Free data.
Okay. ALOS is free. Yeah.
I'm talking on Indian product only. So Cartochet series of data.
That's the best you can say, or that's the maybe any other product which for other usage. Like I need one product, yeah. So Cartochet is the best.
Cartochet, yes, is giving highest resolution.
Okay.
I need hourly data sets for my debris flow modeling, which is not possible for now to get from meteorological agencies. So I use the global precipitation monitoring satellite data, rainfall data.
Rainfall.
Being a groundwater like hydrogeologist, I would say Landsat data till are the best.
Okay.
All 7 bands.
Okay.
Landsat data.
Wonderful. Thank you. Landsat. Sir.
Sir, satellite images I rely on it. IMD rainfall also, though it is not satellite, but I rely on it.
Thank you.
Sir, it actually, your question is very tricky because the choice of product will depend on my application.
Right.
So primarily for my applications, I am using Landsat and I very well agree with him. No beating it. And then secondly, I also use MODIS for my snow and glacier studies.
Very good. Thank you. Any application you use?
Like, of course, one of the best products is our GPS that all of us are using. And from our Indian point of view, I hope that our Navig system which we are developing will have much more better accuracy than any other GPS system. Because one of the this project I am working with Dibrugarh University,
okay,
where we are using the NOAA satellite data.
NOAA satellite.
And we are working on the total electron content in the ionosphere. So the ionosphere anomaly actually impacts the path of that signal, which finally impacts the GPS.
Perfect.
So that is one of the
good product. Thank you so much. I think
I have a quick question to him.
Yeah.
Sir, will we ever get handsets based on Navig for public use?
Certainly. Get one day.
Thank you.
Small example again.
Sure.
When we started, in our phone used to be GPS. Then it started converting to GLONASS.
Right.
And then sometime we get Baidu also. But I think I hope that we'll have that now.
Thank you very much. I really want to thank all the panelists and all the audience to at least maybe not directly asking questions, maybe asking through, sir. So really want to thank everyone. I would also like to add from my side a fantastic job done by the IWRD office department in terms of developing this SWIC. I really congratulate. We really appreciate the way you envisage that the vision of that website is very good. And I think the space products can be linked to those websites, as you are saying that land use land cover map, and so that is a fantastic, and I congratulate for you and that a very well done website, and I hope to adding on the material. So I think with this, I would like to end this panel discussion here. Thanks to all the panelists and all the presenters for really sharing your experience and their knowledge with all the students. Thank you very much.
Hello. Hello. Thank you, experts, for sharing with us your knowledge and your expertise. Now, moving on to the very last segment of today's workshop, let us call up to the stage the Superintending Engineer of IWRD, Sri Bezoziti Azio, to give a closing remark.
It's been a long and hectic day, so I'll make it short and brief. I, on behalf of Irrigation